Good evening and welcome to The Sleepy Scientist. Tonight, as the world outside grows quiet, take a deep breath, settle into your pillow and let your mind drift toward the edge of everything. Because this evening's journey begins at the very start of time itself. We'll be exploring the Big Bang explained slowly, the calm story of how everything you know and everything you'll never see came from a single searing moment of creation. Before we begin, I'd love to know, where in the world are you watching from tonight? Whether it's under city lights, in the countryside, or somewhere in between, it's a pleasure to have you here. And if you're new to The Sleepy Scientist, please take a second to like this video and subscribe. It helps these calm explorations reach other curious dreamers like you. To those of you who've already joined our little constellation of subscribers, thank you. You're the reason these journeys keep expanding. And if you haven't already, tap the notification bell so you don't miss the next slow drift through science and wonder. Now, I do hope this video isn't so interesting that it keeps you awake. But if it does, well, at least you'll be lying there, quietly learning how the universe began. So as you relax, let's travel back, not just billions of years, but before years existed at all, when nothing yet moved, when light had nowhere to shine, and when a single question waited to be asked. How did something so vast begin from almost nothing at all? Before there were stars, before galaxies, before even time itself, there was mystery. For most of human history, people looked at the night sky and believed it had always been there. Eternal, unchanging, a ceiling stretched over the world. The idea that the universe had a beginning, a single fiery birth, would have sounded impossible. In ancient times, creation stories fill that gap. Gods forging the heavens, cosmic eggs cracking open, endless cycles of death and rebirth. Beautiful myths, but all whispering the same intuition, that something started it all. Then, slowly, science began to listen to the light itself. In the early 20th century, astronomers noticed something extraordinary. Distant galaxies were not standing still. They were drifting apart, carried by the stretching fabric of space itself. It wasn't the galaxies that were racing through the cosmos. It was space that was expanding between them. And if everything was once closer together, what happens if you rewind the clock? You reach a time when everything we see, every atom, every photon, every possibility, was squeezed into a single, impossibly hot, impossibly dense state. That idea became known half-jokingly as the Big Bang, a name that stuck, even though there was no bang at all, just an expansion, smooth and silent as the universe began to unfold. The evidence arrived piece by piece, the faint echo of that first light still glowing in the microwave sky, the patterns of the lightest elements forged in the universe's first minutes, and the quiet precision of galaxies moving just as the equations predicted. 3 independent clues, all pointing back to one breathtaking conclusion: that everything began from almost nothing. Over the next chapters, we'll walk through that story slowly, step by step, from the first trillionth of a second to the birth of stars, and finally to the modern universe still expanding above you tonight. No math marathons, no racing thoughts, just calm, careful curiosity. Because when you trace the universe back to its first spark, you discover not chaos, but an astonishing order, a pattern so simple it built everything. So let's begin. At the very first moment of time, the phrase Big Bang sounds dramatic, like fireworks, cymbals, and a cosmic drum roll. But the name, as it turns out, is one of astronomy's most misleading bits of marketing. It wasn't coined to excite the public. It was meant as a joke. In 1949, British astronomer Fred Hoyle said it on the radio while describing a theory he didn't believe in, a universe that supposedly began with a big bang. He meant it as a jab, The name's stuck and science has been patiently clarifying it ever since, because the Big Bang wasn't an explosion in space, it was an expansion of space itself. There was no centre, no fireball sitting in empty darkness, and no edges for the blast to reach. Instead, everything, matter, light, even the dimensions of space, was once closer together and then began to stretch. Imagine dots drawn on a balloon. As the balloon inflates, the dots move apart, not because they're racing across the surface, but because the surface itself is growing. Now, replace the rubber with the entire three-dimensional universe, and you've got the general idea. If that sounds strange, it's because our brains evolved to picture explosions, localized, directional, noisy. But space doesn't behave like that. The universe isn't expanding into something. The distance between all things is simply increasing. Galaxies aren't flying through space like shrapnel. They're passengers on an ever-expanding fabric. You can even see the stretching in the light itself. As space grows, the waves of light travelling through it get stretched too, turning their colour redder. Astronomers call this red shift, and it's one of the simplest fingerprints of a growing universe. So where's the centre of it all? That's the trick question. Every observer, no matter where they are, sees other galaxies moving away in every direction. From Earth, it looks as though we're at the middle of the action. But if you were to teleport to a distant galaxy billions of light years away, you'd see the same thing from there. Everything receding from you too. The universe doesn't have a single centre point. It's more like a rising loaf of bread dotted with raisins. As the dough swells, every raisin sees all the others moving away, and each one could reasonably claim to be in the middle. No offence to raisins, but they make surprisingly good cosmologists. This raises another subtlety. When we talk about the universe, we often mean the observable universe, the region from which light has had time to reach us since the beginning. Light has a finite speed, about 300,000 kilometers every second, and the cosmos has a finite age, roughly 13.8 billion years. Multiply those together and account for expansion, and you get a visible bubble roughly 93 billion light-years across. Beyond that horizon, there are regions we'll never see, at least not yet. They aren't outside the universe. They're simply beyond the part we can observe. It's like standing in a foggy valley. You can only see to the edge of the mist, but you know the hills continue past what your eyes allow. This distinction, observable versus total, is crucial. The Big Bang model describes how the part we can measure behaves, not the totality of all existence. The whole universe could be infinite, curved back on itself, or something stranger still. The point is that everywhere within it once shared a common, denser past. At its heart, the Big Bang isn't a story about a single fiery point in space. It's a story about change, a universe that used to be hotter, denser and smaller, and has been cooling and expanding ever since. The equations of general relativity, when applied to an evenly filled cosmos, predict this behaviour naturally. It's as if the universe can't help but stretch under its own energy, like dough rising under the warmth of the oven. This expansion isn't fast or slow in any everyday sense. It's described by a relationship called the Hubble-Lemaitre law, where the speed at which galaxies appear to recede is proportional to their distance. Nearby galaxies drift away lazily. Far-flung ones race faster. But even those speeds aren't motion through space, they're motion with space. It's a subtle but important shift in perspective. And it means the Big Bang is less a single instant and more a continuous process. The early universe wasn't just a moment ago, it's woven into every photon of ancient light still streaming past us. The cosmic microwave background, discovered by accident in 1965, is the cooled remnant of that first light, a whisper from when the universe was less than 400,000 years old. Every second, those microwaves bathe the Earth, a reminder that the bang never really stopped. It just faded into background music. When you step outside on a clear night and see the stars, you're looking across time, but also across the flow of expansion. The light from distant galaxies began its journey when Earth itself didn't exist, yet the space between you and those galaxies is stretched all the while. The further back you look, the closer everything once was. If you could rewind the cosmic film, galaxies would converge, stars would unform, atoms would split, and even the particles inside them would merge into a brilliant plasma. Eventually you'd reach a frame where physics itself hesitates, a state so dense and uniform that our current laws blur into speculation. That's what we mean by the Big Bang's beginning. Not an explosion we missed, but the earliest chapter our science can still read. So the next time someone pictures the Big Bang as a colossal firework bursting in blackness, you can gently correct them. There was no outside, no edge, no bang echoing through a void. There was only a universe everywhere at once, growing, cooling, and unfolding like a slow cosmic sunrise. And all the galaxies, all the stars, all the planets, all the quiet nights to come were written into that expansion from the start. In short, the Big Bang isn't the story of where the universe began. It's the story of how it changes. A rhythm, not a blast. The universe doesn't sit inside space. It creates space as it grows. Every second that passes, more of reality is born between the stars. And though it began in mystery, its meaning is simple enough to fit into a single, sleepy thought. Everything is still expanding, everywhere, all the time, and somehow we're part of it. The story of the expanding universe began not with a telescope gazing at something new, but with a quiet pattern hiding in starlight. In the early decades of the 20th century, astronomers were collecting the light from distant galaxies, still called spiral nebulae at the time, and passing it through prisms to separate it into rainbows. They expected variety, a scatter of colours, perhaps signatures of different chemical elements. What they found instead was consistency. Each galaxy's spectrum contained the same familiar lines, but every one of them was shifted toward the red end of the rainbow, as though the light itself had been stretched during its journey to Earth. This subtle reddening, known as redshift, was the first hint that something enormous was happening. It was Edwin Hubble, building on the mathematical work of Georges Lemaitre, who connected the dots. The farther away a galaxy was, the greater its redshift seemed to be. It wasn't a random smear. There was a pattern, a neat correlation. The relationship became known as the Hubble-Lemaitre law. A galaxy's apparent speed of recession increases with its distance from us. Hubble's telescope wasn't just showing new galaxies, it was showing that the entire universe was on the move. But what exactly does it mean for a galaxy to be moving away? The phrase can be misleading. These galaxies aren't blasting through space like cosmic rockets. The space between them is stretching. It's a little like walking on an airport moving walkway that's slowly lengthening beneath your feet. You don't feel yourself racing forward, but glance behind you, and everything seems to drift away, pulled by the motion of the walkway itself. In this case, the walkway is the fabric of the universe, and we're all just standing on it. The redshift works as a kind of cosmic Doppler effect. Just as the pitch of a siren drops as an ambulance drives away, the wavelength of light lengthens as the source of that light recedes. Or, in this case, as the space it travels through expands. The waves don't just leave the galaxy and travel through static emptiness, they ride the ever-stretching fabric of the cosmos. By the time they reach Earth, the light's rhythm has slowed, its colour reddened, and its message clear. The universe is growing. To make sense of this pattern, astronomers needed a way to measure distances, and that proved trickier than it sounds. Measuring the distance to a galaxy billions of light years away is not like pacing out steps to the mailbox. astronomers had to build what's affectionately called the cosmic distance ladder, a chain of indirect methods, each calibrated by the rung before it. The first rung involves nearby stars whose brightness we understand well, such as Cepheid variables. These are stars that rhythmically pulse, brightening and dimming with a regular beat. The speed of their pulse tells astronomers their true brightness, which can then be compared to how bright they appear in our sky to calculate their distance. Hubble used these stars in nearby galaxies to anchor the lower steps of his ladder. Further out, where even those stars become too faint to see, astronomers use other standard candles, objects so reliably bright that they serve as universal yardsticks. Among the most famous are Type I supernovae, the cataclysmic deaths of white dwarf stars. They all shine with nearly identical luminosity at their peak, like cosmic light bulbs of known wattage scattered through the dark. By comparing their true brightness with their apparent brightness, astronomers can tell how far away they are. Combine that distance with how redshifted their light appears, and you have a ruler and a speedometer rolled into one. Each rung of the distance ladder adds confidence, but also complexity. Every step comes with uncertainty. Small errors in calibration, assumptions about the stars themselves, or the dust that dims their light. But when several independent methods converge on the same numbers, scientists know they're seeing something real. It's a careful kind of cross-checking that turns faint smudges of light into measurements of cosmic scale. The first time Hubble plotted distance against redshift, the line through his data points was steep. He calculated that the galaxies were flying apart faster than they actually are. His early estimates of the expansion rate, what we now call the Hubble constant, were off by more than an order of magnitude, but the slope of the line was less important than the fact that there was a line. The farther away the galaxy, the faster it appeared to recede. The message was unmistakable. The universe is not static. It's dynamic, evolving, alive in motion. When this realization sank in, it changed everything. Until then, even Albert Einstein had resisted the idea of an expanding cosmos. His equations had hinted at it, but he assumed that the universe must be eternal and unchanging, so he added a cosmological constant to hold it still. Later, when the evidence for expansion became undeniable, he reportedly called that adjustment his greatest blunder. It's a charming reminder that even geniuses sometimes cling to the familiar. As the decades passed, better telescopes refined the numbers. Space-based observatories freed astronomers from atmospheric distortion, allowing sharper images and more precise measurements of distant supernova. Radio telescopes mapped the cosmic microwave background, the faint afterglow of the early universe, and those patterns matched beautifully with what an expanding model predicted. Step by step, the ladder reached further, and the conclusion held firm. Today, when we look across billions of light years, we see galaxies receding at astonishing speeds. The light from some is shifted so far into the infrared that only specialized instruments can detect it. Yet we know these apparent velocities aren't traditional motion. They're a reflection of expansion itself. Two galaxies separated by twice the distance will have twice the redshift. It's a beautifully simple proportionality, a rhythm underlying the universe's growth. If you could somehow pause the expansion, freeze the cosmic walkway, you'd see galaxies more or less holding their positions in space, bound to their local clusters, not racing outward like fireworks. The movement we observe is embedded in the fabric itself. That's why there's no central point of departure, no direction you can travel to find where it all started. Every point is expanding away from every other point. Wherever you stand, you're at the center of your observable universe. Still, measuring the exact rate of this expansion remains one of the great challenges in cosmology. Different methods sometimes yield slightly different numbers, leading to what scientists call the Hubble tension. One group, using the distance ladder built from Cepheids and supernovae, finds a rate a few kilometers per second faster than what the cosmic microwave background suggests. The discrepancy is small but persistent, and it keeps researchers both humble and curious. It's a sign that even a century after Hubble's discovery, the universe still has secrets folded into its light. The beauty of this story is how it began with a handful of fuzzy photographs and a pattern no one expected. What seemed like static pinpricks of light turned out to be messages from the past, stretched by time itself. Each photon arriving at your eye or telescope lens has travelled across billions of years, its wavelength stretched by the swelling of space. You could say the universe is still whispering the same tune Hubble first heard, a deep cosmic note that grows lower as the ages pass. If you could listen to that sound, it would be silence, the hush of expansion continuing without end. The galaxies are not rushing through the void itself is breathing, widening, carrying them gently apart. That's what the redshift tells us. Not chaos, not explosion, but an elegant stretching. A universe growing old gracefully, like the slow rising of a tide that began long before the first wave reached the shore. Every story has an old photograph tucked away somewhere, a snapshot of how things began. For the universe, that photograph isn't tucked into an album, it's stretched across the entire sky. It's called the cosmic microwave background, or the CMB for short, and it's the oldest light we can see. It's not starlight, or even the glow of galaxies, but the faint afterglow of the universe itself, light released when everything was still young, hot, and unimaginably bright. To understand what this light really is, picture the universe roughly 380,000 years after its beginning. Back then it was dense, fiery, and full of particles, protons, electrons, photons, all jostling in a thick glowing fog. Photons of light couldn't travel freely because they kept bumping into charged particles, constantly scattering, absorbed and re-emitted in an endless dance. The whole cosmos was, in essence, opaque. It wasn't that light didn't exist, it just couldn't get very far before being bounced around again. Then, as the universe expanded, it cooled. And in that cooling came a moment of clarity. When the temperature dropped to about 3,000 degrees, protons and electrons could finally join together to form neutral atoms. That simple act, electrons finding homes around nuclei, suddenly changed everything. Without free electrons constantly scattering light, the universe went from opaque to transparent almost overnight. Photons could finally travel freely, unimpeded for the first time in cosmic history. Astronomers call that moment the last scattering. Those first free photons are still travelling today, their energy stretched and softened by more than 13 billion years of cosmic expansion. What was once a searing orange-white glare has been stretched until it now hums gently in the microwave range, a form of light far beyond what human eyes can see. If your eyes could tune into microwaves, the entire sky would glow with a nearly perfect uniformity, a pale wash of warmth coming from every direction. The CMB isn't just an abstract concept, it's real, measurable radiation filling all of space. It's everywhere, between the stars, behind the galaxies, even inside your living room. If you ever use an old television with a fuzzy signal, about 1% of that static came from this ancient light. Those little specks of noise were photons that had been travelling since the dawn of time, bouncing off your TV antenna just before they reached the end of their 13 billion year journey. At first glance, the cosmic microwave background looks astonishingly smooth. No matter where you look, it has the same temperature, about 2.7 degrees above absolute zero. That kind of uniformity is one of the great wonders of nature. Across distances of billions of light years, the temperature barely varies by a few millionths of a degree, yet hidden in those tiny ripples are the seeds of everything we see today. Those faint variations, slightly warmer and cooler patches, represent regions of slightly higher or lower density in the young universe. Where it was just a little denser, gravity began to gather matter, and over billions of years those tiny fluctuations grew into galaxies, clusters, and vast cosmic webs. It's humbling to think that every star, every planet, and every night sky trace back to small wrinkles in the texture of that ancient light. Detecting the CMB wasn't something scientists originally set out to do. In the early 1960s, two engineers, Arno Penzias and Robert Wilson, were testing a radio antenna in New Jersey for satellite communications. No matter how carefully they cleaned it or adjusted it, they couldn't get rid of a faint background hiss. They thought it might be interference from the city, or even pigeon droppings inside the antenna horn, an indignity they addressed with remarkable dedication. Yet the hiss remained. Meanwhile, just 30 miles away, a group of physicists at Princeton University had been preparing an experiment to look for exactly such a signal, the residual glow from the early universe that theoretical models had predicted. When Penzias and Wilson learned about that theory, they realized their troublesome static was actually the oldest light in existence. It was one of those wonderful scientific moments where confusion turns into revelation. The engineers had stumbled upon the cosmic afterglow of creation. Over the next few decades, astronomers refined those first, rough measurements. Ground-based detectors were limited by Earth's atmosphere, so the search for precision moved to space. In 1989, NASA launched the Cosmic Background Explorer, or COBE, which mapped the CMB in detail for the first time. It confirmed that the radiation followed an almost perfect blackbody spectrum, exactly what theory had predicted for light cooled by billions of years of expansion. The discovery earned John Mather and George Smoot the Nobel Prize in Physics, and cemented the Big Bang model as the leading explanation for our universe's origin. But COBE was just the beginning. In 2001, the Wilkinson Microwave Anisotropy Probe, or WMAP, launched to take an even closer look. WMAP revealed those tiny ripples, the minute temperature differences across the sky, with stunning clarity. What had seemed uniform before was now a map of delicate texture, a baby picture of the cosmos in exquisite detail. From that map, scientists could infer the universe's age, composition, and shape. A decade later, the European Space Agency sent up Planck, an even more sensitive satellite with finer resolution. Planck's data refined our understanding still further, narrowing the age of the universe to about 13.8 billion years, and confirming that its geometry is remarkably flat, not curved. It also measured, with extraordinary precision, how much of the cosmos is made up of ordinary matter, dark matter, and dark energy. All of that, everything we know about the universe's overall structure, emerged from the faint pattern of light released when it was less than 500,000 years old. When you see the colourful map of the CMB, often painted in blues and reds, remember that those colours are exaggerations. The real variations are only a few 10,000ths of a degree. Yet those slight imperfections are everything. Without them, the universe would have remained a uniform mist. There would be no galaxies, no stars, no one to look back and wonder. The ripples in the microwave background are literally the blueprint of cosmic structure. The cosmic microwave background is not only a relic, it's also a ruler. By studying its pattern of ripples, scientists can measure the size of the universe, its rate of expansion, and even its long-term fate. The peaks and valleys in the CMB's temperature map correspond to acoustic waves, pressure oscillations that rippled through the hot plasma before light was freed. Those sound waves, frozen into the fabric of the universe, act as a cosmic yardstick that helps astronomers measure distances across billions of light years. It's as though the universe left behind a faint soundtrack of its own beginnings, one we can still read today in the pattern of the sky. What makes the CMB so beautiful is its dual nature. It's both incredibly ancient and eternally present. Every direction you look, you're gazing at the same moment in time, when the cosmos first became transparent. In that sense, the CMB is the nearest thing to a photograph of the birth of light itself. When you stand outside on a dark night, every photon that touches your skin carries a story, but the oldest of them, still humming faintly in microwaves, tells the first story of all. That whispering glow is the universe's memory. It fills every corner of space with the soft aftertaste of its fiery youth. 13 billion years ago, those photons began their journey, and tonight they are still arriving, one by one, gentle and patient, the oldest travellers in existence. If you could rewind the universe to its first few minutes, you'd witness the most intense chemistry lesson imaginable, one that set the stage for everything that would ever exist. The cosmos, still glowing with unimaginable heat, was not yet filled with stars or galaxies or even stable atoms. It was a swirling plasma of protons, neutrons, electrons, and light, all colliding, forming and breaking apart in a furious cosmic soup. Yet, in that chaos, the first atomic nuclei, the heart of all matter, were quietly being born. This brief but crucial period is known as primordial nucleosynthesis, or more simply, the universe's first chemistry experiment. It happened between about 1 second and 20 minutes after the beginning, a blink in cosmic time, but one of the most productive blinks in history. The temperature dropped from the unimaginable energy of the first instant to something still staggeringly hot, roughly 1 billion degrees. At that point, the universe was finally cool enough for protons and neutrons to stick together, instead of being instantly blasted apart. The very first ingredient was hydrogen, made of single protons. Hydrogen would remain the simplest and most abundant element in the universe, but in those first minutes some of those protons met their neutron partners. When that happened, they fused into a heavier nucleus called deuterium, also known as heavy hydrogen. Add another neutron and another proton, and you get helium-4, the same helium that fills balloons today. A tiny fraction went a little further to make helium-3, and an even smaller sliver managed to form lithium-7, the lightest metal. And that was about it. The early universe only managed to build those lightest few elements. The temperatures and densities dropped too quickly for heavier ones to form. There just wasn't enough time. After about 20 minutes, the cosmic furnace had cooled so much that nuclear fusion stopped altogether. The universe was left with a mixture that would persist for billions of years. About 75% hydrogen, 25% helium, and mere traces of deuterium, helium-3, and lithium. Those numbers may sound simple, but they are incredibly precise fingerprints of how the early cosmos behaved. It's worth pausing to picture what those moments were like. The universe was expanding rapidly, but not empty. Every cubic centimetre contained billions of particles, still glowing and colliding at unimaginable speeds. Photons of light were everywhere, keeping the soup hot and energetic. Neutrons, which are unstable on their own, were gradually decaying into protons, but not before some of them found partners to form nuclei. It was a frantic race against time. The faster the universe expanded and cooled, the fewer chances the neutrons had to bind. If the balance of forces had been even slightly different, the chemical makeup of everything we know would have turned out completely differently. Why did the process stop with helium and lithium? Because making heavier elements requires a delicate balance of conditions, specifically a long period of stable heat and pressure. In stars, that balance is provided by gravity, which keeps fusion going for billions of years. But in the early universe, there were no stars yet, and gravity hadn't had time to pull matter into dense clumps. The expansion was relentless, dragging everything apart before atomic nuclei could grow beyond the lightest elements. The cosmic chemistry lab slammed shut almost as soon as it opened. This means that every atom of helium you breathe today, and every bit of deuterium hiding in Earth's oceans, was forged not in a star but in those first 20 minutes. They are truly primordial, ancient relics from when the universe itself was a nuclear reactor. If you could somehow bottle that early plasma, you'd be holding the original recipe for matter, straight from the dawn of time. Decades after this process was first proposed, scientists began to test whether the theory held up. They could measure the abundances of these light elements in the oldest stars and in the most pristine gas clouds, the ones least contaminated by later stellar activity. What they found was almost spooky in its precision. The ratios predicted by Big Bang nucleosynthesis matched what astronomers observed. The helium fraction, the amount of deuterium, and even the faint trace of lithium all lined up remarkably well with theory. This was the universe's first quality control check. If the numbers hadn't matched, it would have meant the model was missing something fundamental. Instead, the match was so good that it confirmed not just the chemistry, but also the conditions of the early universe, its density, temperature, and even the number of types of light neutrino-like particles buzzing around at that time. It was as if the cosmos had kept a detailed record of its own infancy, written in the language of isotopes. The elegance of this process is that it's testable. Astronomers can look billions of years into space, studying regions where the gas remains nearly untouched since the beginning. Those measurements allow them to check the predictions again and again. The deuterium abundance, in particular, serves as a sensitive indicator of how fast the universe expanded in its first minutes. It's one of the many independent ways scientists have confirmed the same story, told by the redshift and the cosmic microwave background. Of course, a few small mysteries remain. The predicted amount of lithium doesn't quite match what we observe in old stars. It's a little too high. This lithium problem, as it's affectionately called, is one of those puzzles that keeps cosmologists curious. It could hint at subtle new physics or simply reflect processes that altered lithium in the earlier stars. Either way, the overall agreement between theory and observation remains extraordinary. It's astonishing to realize that by studying the faintest traces of light and the simplest atoms, we can reconstruct what happened when the universe was less than half an hour old. Those first chemical reactions created the raw ingredients for everything that followed. Hydrogen for stars to fuse, helium for them to burn into carbon, and just enough lithium to season the cosmic mix. Everything heavier, oxygen, iron, gold, had to wait billions of years until stars were born, lived and died, scattering their enriched ashes across space. The universe's first chemistry was simple, but it built the foundation for all later complexity. If the early universe were a recipe, it would read something like this. Take 1 part hydrogen, add a 1/4 part helium, stir in a trace of deuterium, and sprinkle the tiniest pinch of lithium. Mix under high heat for 20 minutes, then allow to cool for the next 13 billion years. Serve with stars, galaxies, and a side of wonder. This simple mixture is what astronomers still find today when they look far back in time. Clouds of primordial gas, untouched by generations of stellar fusion, still carry that same composition. They act as fossils from the first moments of creation. And when those numbers are plotted against the theoretical models of nucleosynthesis, the curves line up almost perfectly. It's one of the cleanest confirmations in all of science, a story that fits together across vastly different kinds of evidence. You can think of it this way. The expansion of space shows us the universe is still stretching. The cosmic microwave background shows us its first light, and the light elements show us its first matter. 3 separate clues, discovered in different ways, all pointing to the same beginning. Each on its own would be compelling. Together, they form a portrait too consistent to ignore. The next time you look up at the night sky, remember that much of what you see began in those first 20 minutes. The helium shimmering in distant stars, the hydrogen fueling the sun, even the trace elements that make up life. They all carry the memory of that first fire. The cosmos began with light, but it also began with chemistry. And in those fleeting moments, it wrote the first formula for everything that would ever be. Imagine the universe as a film you could rewind all the way to the first frame, a single flash before the opening credits. What you'd see wouldn't be stars or even light, but a wild ocean of energy, space, and possibility condensed into something smaller than imagination allows. And then, in less time than it takes light to cross the width of a single atom, everything began to unfold. The earliest period, sometimes called the Planck era, lasted less than a trillionth of a trillionth of a trillionth of a second. It's a place where our current understanding of physics simply runs out of road. Gravity, quantum mechanics, and the other fundamental forces were so intensely intertwined that no theory can yet describe them all at once. It's like peering into the first frame of existence through a frosted window. We can sense that something profound happened there, but the details remain hazy. Still, it sets the stage for everything that followed. After that impossible beginning came the first recognizable event in our cosmic timeline, an astonishingly brief period known as inflation. In a fraction of a heartbeat, the universe ballooned in size by an enormous factor, growing from subatomic to cosmic in what felt like an instant. Space itself stretched faster than light, not because anything was breaking the rules, but because the rules were being written as it happened. Inflation smoothed out the wrinkles, evened the temperature, and spread tiny quantum fluctuations across vast distances. Those infinitesimal ripples would one day grow into galaxies and clusters. As inflation slowed, the energy locked within that rapid expansion poured into the universe as particles and radiation. You could think of it as the cosmos reheating, turning a field of pure energy into a bubbling stew of matter and light. Quarks, the tiny building blocks of protons and neutrons, flickered into existence along with gluons, the sticky force that binds them. The universe was still so hot that nothing could stay together for long. Quarks collided, separated and collided again in a blazing dance called the quark-gluon plasma. At this stage, time could be measured in millionths of a second. The temperature was tens of trillions of degrees, so fierce that the mere idea of a solid surface was meaningless. Space was a glowing soup where matter and energy were nearly interchangeable. Every particle that existed had its equal and opposite partner, matter and antimatter in perfect balance, forever meeting and annihilating in bursts of radiation. Yet by some tiny asymmetry, one extra particle of matter for every billion pairs that destroyed each other, the universe emerged with just enough leftover material to make the stars, planets, and people who would one day ponder it all. As the universe continued to cool, it reached a turning point. Around 1/10,000th of a second after the beginning, quarks finally settled down, joining together to form protons and neutrons. The strong nuclear force locked them in place, creating the stable ingredients that would later fuse into atoms. The era of the quark-gluon plasma faded, replaced by a new stage where recognizable matter began to exist. Now the cosmic temperature dropped to a few trillion degrees, still unthinkably hot, but cool enough for forces to begin distinguishing themselves. The fundamental interactions, gravity, electromagnetism, and the nuclear forces, each took on their modern identities. The universe was playing a slow game of musical chairs. As it cooled, the available seats for certain interactions disappeared, and particles had to find new roles in the unfolding story. By the time the universe was a full second old, neutrinos, those ghostly particles that rarely interact with anything, had slipped free of the crowd. They still zip through you by the trillions every second, silent messengers from that early age. Around the same time, electrons and positrons, the antimatter twins of electrons, continued their furious dance of creation and destruction. Eventually, the temperature dropped enough that most positrons annihilated with electrons, leaving behind a slight surplus of electrons. Those survivors would one day orbit around atomic nuclei and form the structure of every atom in the cosmos. A few minutes later, the next milestone arrived, the beginning of nucleosynthesis, when the first atomic nuclei began to form. The universe had cooled to roughly 1 billion degrees, no longer a blinding plasma, but a glowing, fluid mixture of protons, neutrons, and photons. Under those conditions, hydrogen nuclei could fuse into helium, with traces of deuterium and lithium appearing as well. It was the universe's first attempt at chemistry, a short, intense workshop in the art of making elements. After about 20 minutes, the expansion had thinned the density so much that fusion fizzled out, locking in the ratios of hydrogen and helium that would remain nearly constant across time. From this point onward, the pace slowed dramatically. The universe continued to expand and cool, but the frantic transformation of particles into new forms was largely over. For the next few 100,000 years, the cosmos would remain a glowing fog of free particles and light, with energy still bouncing from one particle to another. It was too hot for atoms to form yet. Photons kept colliding with electrons, scattering endlessly. But the grand pattern was already in place. The idea that all this can be described in such detail might sound like pure speculation, but it's anything but. Each stage in this early timeline leaves measurable fingerprints that scientists can detect today. The abundance of helium tells us about the first few minutes. The cosmic microwave background shows us what happened when light finally broke free, hundreds of thousands of years later. The structure of galaxies and clusters reveals how the tiny fluctuations seeded during inflation grew over time. These are not random guesses. They're testable, repeatable clues stitched together from observation. If it all feels dizzying, there's a simple way to think about it. As the universe cooled, its options narrowed. In the beginning, energy could transform into almost anything. Particles, radiation, fields, all swapping roles freely. But as temperatures fell, fewer transformations were possible. Particles froze into stable forms, forces settled into predictable behaviours, and the chaotic dance slowed into something orderly. Like a game of musical chairs where each round removes more seats, only the most stable combinations remained once the music stopped. When scientists simulate this early evolution, they use physics tested in laboratories, particle accelerators that recreate conditions similar to those first fractions of a second. What they find matches beautifully with the cosmic story told by the sky. That harmony between theory and observation is part of what makes cosmology so elegant. The same equations that describe subatomic collisions can explain how entire galaxies began their journey. By the time the universe was a few minutes old, it had already written most of its rules. Gravity would gather matter into clumps, fusion would light the first stars, space would keep stretching, carrying everything farther apart but never pulling it completely out of reach. All of this was set in motion in those first fleeting instants, when the universe was still learning what it meant to exist. It's humbling to remember that every atom in your body can trace its ancestry back through that sequence, through the brief flash of nucleosynthesis, through the quark soup, through the inflationary surge, and even further into the mystery before physics itself took shape. We're made of particles that froze out when the universe was barely a heartbeat old, atoms that formed when it was a toddler, and starlight that matured when it reached its cosmic adolescence. The entire timeline, from the tiniest fraction of a second to the first 20 minutes, isn't just ancient history. It's the opening chapter of everything that followed. And it all began quietly, with the universe cooling and expanding, playing its long game of musical chairs until the last piece of matter found its seat. If the Big Bang is the grand opening of the universe, then inflation is the mysterious overture that set the tone before the first note was even played. It's the idea that, in a tiny sliver of a second after the beginning, the universe didn't just expand, it exploded in smoothness. Space itself ballooned at a breathtaking rate, faster than anything we can easily imagine. And while that might sound like science fiction, inflation was proposed not to make the story more exciting, but to fix a few puzzling questions that the original Big Bang model couldn't quite answer. The first of those puzzles is called the horizon problem. When scientists looked at the cosmic microwave background, the afterglow of the early universe, they found it to be astonishingly uniform. No matter which direction you look, the temperature is almost exactly the same. But here's the riddle. Those opposite sides of the sky are so far apart that, according to standard expansion, there hasn't been enough time since the beginning for light or heat to travel between them. It's as if two people started baking cookies in opposite corners of the universe without ever meeting, yet somehow ended up using the same recipe and oven temperature. How did such distant regions end up so perfectly coordinated? The second issue is known as the flatness problem. When scientists talk about the shape of the universe, they mean its geometry, the way parallel lines behave over cosmic distances. The equations of general relativity allow for a universe that could be positively curved, like a sphere, negatively curved, like a saddle, or flat, like a sheet of paper. Observations show it's extremely close to flat. But flatness is unstable. If the early universe were even slightly curved, that curvature would have grown over billions of years. The fact that it's still flat today implies that it must have been unimaginably, almost impossibly flat at the start. Why would the universe begin with such fine-tuned precision? The third puzzle has an equally exotic name, the monopole problem. Certain theories of physics predict the existence of magnetic monopoles, hypothetical particles that carry only a single magnetic pole, north or south, rather than both. They should have been produced in abundance in the early universe, yet despite decades of searching, we've never found a single one. Either nature hid them extraordinarily well, or something about the early universe diluted them out of existence. Inflation offers an elegant solution to all three puzzles in one sweeping move. The idea, first proposed by physicist Alan Guth in the early 1980s, is that a fraction of a second after the beginning, something like 1/10 billionth of a trillionth of a trillionth of a second, the universe underwent a brief but staggering burst of accelerated expansion. Space itself stretched exponentially, growing by an absurd factor, perhaps by as much as 10 to the power of 70 in size, in less time than it takes to blink. During this inflationary moment, regions that had once been close enough to exchange heat and light were suddenly whisked far apart. That explains the horizon problem. Before inflation, everything was in contact, sharing the same conditions. Inflation didn't create smoothness. It preserved it while stretching space beyond all communication. As for flatness, inflation naturally flattens the geometry of space, just as blowing up a small balloon makes its surface seem smoother and less curved. And those elusive monopoles, they may still exist, but inflation would have scattered them so widely that any single observable universe like ours would contain essentially none. 3 cosmic riddles, one graceful answer. It's worth emphasizing what inflation isn't. It's not a regular explosion. There was no fiery center pushing matter outward into empty space. Instead, space itself expanded, dragging everything along for the ride. Imagine the fabric of the universe as a rubber sheet covered in dots. Inflation would be like that sheet being stretched so rapidly that the dots, representing tiny regions of space, raced away from each other faster than light. Nothing was breaking the speed limit, because the rule applies to things moving through space, not to space itself expanding. It's not that galaxies were speeding away through the cosmos was swelling between them. Inflation also introduces one of the most poetic ideas in cosmology, that the tiny quantum ripples in energy that existed before inflation were stretched across the universe, becoming the seeds of all structure. Quantum mechanics tells us that even empty space is restless, fluctuating ever so slightly at the smallest scales. When inflation blew up the universe, those microscopic wiggles were magnified into vast ripples in density, laying down the blueprint for galaxies, stars, and everything else that would form later. Every swirl of a galaxy cluster today can trace its ancestry to a flicker of uncertainty that once fit inside a subatomic speck. These predictions aren't just armchair theorizing. They leave measurable fingerprints. The pattern of tiny temperature variations in the cosmic microwave background matches exactly what inflation predicts. Slight Gaussian ripples that are nearly scale invariant, meaning they look the same on large and small scales. Those subtle fluctuations, mapped by satellites like WMAP and Planck, are essentially the after-echoes of quantum jitters from the universe's earliest instant. The data doesn't just support inflation, it practically hums its melody. That said, cosmologists approach inflation with humility. It's a powerful idea, but still a model, a story supported by evidence, not a divine decree. Alternative ideas exist. Some physicists explore bouncing cosmologies, where a previous universe collapsed and rebounded into ours. Others propose cyclic models, where cosmic history repeats in endless expansions and contractions. There are even theories suggesting that what we call inflation might be part of a larger multiverse, with countless bubble universes expanding in different ways. These are bold possibilities, but so far none match the observational data as cleanly as inflation does. The strength of inflation lies in how much it explains with so little. It doesn't require new exotic forces beyond what physics already allows. Just a brief episode where a field of energy dominated the universe and then decayed, releasing its stored energy into particles and radiation. When that happened, the familiar Big Bang expansion took over. The inflationary stage ended quietly, leaving behind a universe smooth enough, flat enough, and large enough to match everything we observe. If the early universe were a symphony, inflation was its first, nearly silent movement, a crescendo so brief you could miss it entirely, yet powerful enough to define the rhythm of everything that followed. It transformed a microscopic patch of space into a cosmos capable of containing galaxies, stars, and time itself. And though it lasted for only the tiniest fraction of a second, its legacy fills the sky we see every night. What makes inflation so captivating is how it blends simplicity with wonder. The math is intricate, the physics subtle, but the picture it paints is beautifully intuitive. A universe born from smoothness, expanded by a whisper of energy, and seeded by the randomness of quantum fluctuations. Every cosmic structure, from the Milky Way to the faintest cloud of gas, owes its existence to those tiny quantum ripples stretched across a newborn sky. In the end, inflation is not just a solution to cosmic puzzles, it's a reminder of how the universe turns chaos into structure and how vast order can emerge from the briefest flash of uncertainty. Whether inflation is ultimately the full truth or just the best version we have for now, it remains one of science's most astonishing insights. That everything we see began with a quiet surge, a moment of expansion so brief and so profound that even today, the universe is still catching its breath. When inflation finally came to an end, the universe faced a peculiar problem. It was enormous, smooth, and eerily empty. The incredible burst of expansion had stretched space to vast proportions, but in doing so, it had also diluted everything to almost nothing. The cosmos was cold and quiet, filled not with matter and light, but with a kind of vacuum energy left over from the field that drove inflation. To build stars, planets, and eventually curious beings able to ask where they came from, the universe needed a way to turn that energy back into substance. The solution was both elegant and explosive: reheating. Reheating is the stage when the energy that powered inflation decayed into the familiar ingredients of the cosmos: particles, radiation, and heat. If inflation was like pulling back a cosmic bowstring, then reheating was the moment it was released, sending its stored energy cascading into everything that would follow. In that instant, the universe went from near silence to a roaring, glowing bath of creation. To imagine it intuitively, picture a tightly wound spring. During inflation, that spring was compressed beyond comprehension, storing an immense amount of potential energy in the fabric of space itself. When inflation ended, the spring snapped back, releasing its energy as motion and warmth. Space filled with particles popping into existence: electrons, quarks, neutrinos, and photons, bouncing and colliding in a frenzy of new beginnings. The universe became hot again, hotter than any star that would ever shine within it. That's why cosmologists describe the early universe as reheated. Inflation had chilled it, not in the everyday sense of temperature, but in terms of its particle content. The expansion was so extreme that it left behind a vacuum, a vast stretched field with almost no matter to speak of. The sudden decay of the inflationary field released its stored energy into a torrent of radiation, restoring the fire. It's a bit like a balloon suddenly deflating into heat and light, except the balloon is space-time itself. Within fractions of a second, the temperature soared to unimaginable heights, perhaps 10 trillion degrees or more. Everything was now a dense plasma of energy and particles, but this time the expansion was gentler, slower, and more predictable. The universe was no longer inflating faster than light. It had transitioned into the kind of steady expansion that defines cosmic history today. It was, at last, the kind of place physics could comfortably describe. What makes this transition so remarkable is that it represents the universe's first great transformation of energy into matter. The field that had driven inflation, whatever its exact nature, lost its dominance, and in its place appeared the familiar cast of cosmic characters. Matter and antimatter pairs formed and annihilated in a delicate balance, while photons filled every corner of space, bouncing from one particle to another. These photons, endlessly scattering, would remain trapped in that plasma for hundreds of thousands of years before escaping as the light we now see as the cosmic microwave background. Reheating also marked the beginning of the universe's first real thermodynamics, a time when temperature, density, and pressure meant something tangible. Before that, during inflation, the concept of temperature was meaningless. There were no particles to share heat, no collisions to spread energy around. But now, with countless new particles interacting, the cosmos could finally act like a giant glowing gas. In those moments, the universe became not just an expanding mathematical space, but a physical system in motion, a place where heat flowed, entropy increased, and time began to feel directional. In the language of physics, the energy of the inflationary field decayed into radiation and particles, In everyday terms, it simply meant that the stored potential energy was converted into kinetic energy, the motion and vibration of matter. Every particle that exists today owes its origin to that conversion. Even the humble photon, the particle of light, traces its lineage back to this first bath of radiation. The universe quite literally lit up from within. Though we cannot witness reheating directly, it happened long before light could travel freely. Its effects are still written into the sky. The near-perfect uniformity of the cosmic microwave background tells us that the energy was spread out evenly, while its tiny fluctuations reveal that reheating didn't erase the subtle patterns laid down during inflation. Instead, those ripples in density were carried forward, providing the seeds for all later structure. Over billions of years, that initial radiation cooled and stretched as the universe expanded. The photons that once blazed with unimaginable energy have been stretched into long, gentle microwaves. What was once a furnace filling every point in space is now a faint whisper at 2.7 degrees above absolute zero, the afterglow that surrounds us today. Each of those photons is a cooled echo of that first reheating, still washing over us after more than 13 billion years. You can think of the cosmic microwave background as the universe's memory of this moment, a kind of cosmic fingerprint left by the transition from the inflationary vacuum to a hot, dense plasma. The temperature of that background radiation has fallen as the universe has expanded, but its presence is a reminder that the heat once filled everything. In a sense, the universe has never really cooled off. It has simply stretched its warmth thinner and thinner, letting the same light flow across an ever wider stage. The story of reheating is a testament to the universe's efficiency. It began with almost pure potential, energy stored in an unseen field, and within an instant that potential was converted into the building blocks of everything. It's as if nature took one deep breath, held it through inflation, and then exhaled, filling space with the first spark of matter and motion. Without that release, the cosmos would have remained sterile, smooth, and lifeless, a vast empty stretch of geometry with nothing to fill it. What caused inflation to end and reheating to begin is still a subject of research. It may have been triggered by the instability of the inflationary field, or by quantum fluctuations that caused parts of it to decay faster than others. Whatever the exact mechanism, the transition was graceful. It didn't leave behind a chaotic explosion or a messy aftermath. Instead, it created a nearly uniform universe, just uneven enough to make it interesting. Those tiny irregularities became the scaffolding on which galaxies and clusters would eventually grow. When we look at the sky today, we're seeing the legacy of that first burst of heat. Every beam of starlight, every flicker of energy from a quasar or nebula is part of the same continuum of radiation that began with reheating. The stars didn't invent light, they inherited it. The photons released in those first moments still fill the cosmos, endlessly redshifted, endlessly travelling. They are the quiet descendants of the universe's original fire. If you were to compress all of cosmic history into a single symphony, inflation would be the long, drawn-out note of tension, and reheating would be the sudden release, the triumphant chord that sets everything in motion. It's the moment when emptiness became substance, when energy turned tangible, and when the universe truly became a place that could be warm, bright, and alive. So the next time you feel the sun's warmth or see light scatter through clouds, remember that it all began with that first burst of reheating. The photons that warmed the infant cosmos have travelled across epochs, transforming but never disappearing. The glow we live under now, the cosmic background, the starlight, the gentle hum of radiation, is the aftertaste of that primordial heat. The universe may have cooled since then, but it still carries the memory of its first warmth, softly shining in every corner of the sky. If you could pause the universe at 3 minutes old, you'd be looking at a moment that defined nearly everything to come. In that tiny window of time, the cosmic temperature, density, and timing aligned with exquisite precision, allowing the first nuclei of atoms to form. Everything heavier than hydrogen, every puff of helium in a star, every trace of deuterium in the oceans owes its existence to those fleeting moments. Cosmologists sometimes call this era the first 3 minutes, borrowing the phrase from physicist Steven Weinberg, who compared it to a brief but decisive act in the great play of creation. At 1 second old, the universe was already busy. Protons and neutrons, the basic building blocks of atomic nuclei, had formed from the sea of quarks as the temperature dropped below 1 trillion degrees. For the first time, matter could hold itself together, though barely. The balance between protons and neutrons was set by a delicate interplay between the weak nuclear force and the temperature of the cosmos. When it was hot enough, protons and neutrons freely swapped identities through reactions with neutrinos, but as the universe expanded and cooled, that exchange slowed down. Eventually, neutrons began to decay, turning into protons with a half-life of around 10 minutes. By the time the temperature dropped to the critical point for fusion, roughly 1 neutron remained for every 6 protons. That simple ratio would determine the universe's entire chemical destiny. The first hurdle in nuclear construction came in the form of what scientists call the deuterium bottleneck. Deuterium, or heavy hydrogen, is the first stable step in building heavier elements. It's made when a proton and a neutron fuse together, forming a light but fragile nucleus. The problem was that the early universe was still far too hot. Any deuterium that managed to form was almost immediately smashed apart by the relentless bombardment of high-energy photons. It was like trying to build a snowflake inside a furnace. It would melt as soon as it appeared. But the universe was cooling fast. In less than a minute, its temperature had dropped from billions of degrees to a few 100 million. Once it fell below a critical threshold, about 1 billion degrees, the deuterium nuclei began to survive, and with that breakthrough the door to real element building swung open. Within moments, deuterium fused into helium-3, and helium-3 collided to form helium-4, a nucleus made of 2 protons and 2 neutrons. This was the universe's first stable structure, a foundation so robust that helium-4 would come to dominate all future nuclear reactions. The whole process was a race against time. The window for fusion to occur lasted only a few minutes. If the universe had expanded faster, it would have cooled too quickly for many reactions to take place, leaving a cosmos made mostly of hydrogen. If it had expanded more slowly, it would have stayed hot longer, allowing nearly all protons to fuse into helium, leaving little hydrogen for stars to burn. Fortunately for us, the timing was just right. Roughly 75% of all matter froze out as hydrogen, and 25% as helium, with a smattering of deuterium and lithium. It was a balance perfectly tuned for a universe that would one day sparkle with stars. These numbers might sound like mere trivia, but they set the stage for everything that followed. The ratio of hydrogen to helium determines how stars live and die. Stars are powered by hydrogen fusion. When hydrogen runs out, they turn to helium and beyond. Without that initial mix, the universe's chemistry would have unfolded very differently. Too much helium and stars would burn too fast. Too little, and heavier elements might never form. Those first 3 minutes wrote the recipe for cosmic evolution. As the minutes ticked by, the universe continued to cool and expand. By the 10-minute mark, the nuclear reactions were winding down. The density had fallen, and collisions between particles became rare. Neutrons that hadn't been locked inside helium nuclei decayed away, leaving a universe composed mostly of free protons, hydrogen nuclei, and helium atoms in waiting. The great fire of creation was over, but its ash would fuel billions of generations of stars. One of the most fascinating things about this period is how sensitive it was to temperature. In the early universe, temperature wasn't a gentle gradient. It was a timer, a cosmic clock ticking down. Each nuclear reaction could only happen within a very specific range of heat and density. Too hot, and everything flew apart. Too cold, and nothing could fuse. The entire chemical structure of the cosmos depended on passing through that window at just the right pace. When cosmologists run simulations of this process, even slight changes in the expansion rate or the strength of the forces involved lead to dramatically different outcomes. It's one of nature's most delicate balancing acts. The results of that act are still measurable today. Astronomers can look at distant gas clouds that have never been touched by starlight, primordial reservoirs of matter, and find exactly the same elemental proportions predicted by these early reactions. That agreement is one of the great triumphs of cosmology. It means the physics of nuclear fusion, tested in laboratories on Earth, describes what happened when the entire universe was smaller than a galaxy. It's as if the cosmos and our equations are reading from the same script, written billions of years ago. While the universe's chemistry froze in those first 3 minutes, the consequences have been anything but static. Hydrogen and helium became the raw fuel for stars. In the hearts of those stars, fusion continued the work that nucleosynthesis began, creating heavier and more complex elements, carbon, oxygen, iron, and eventually everything needed for life. But none of that could have happened without the groundwork laid during those earliest moments. The cosmic mix of light elements wasn't just a chemical footnote, it was the foundation of complexity itself. It's humbling to realize how brief this phase was in comparison to the vastness of cosmic time. In a human lifetime, 3 minutes can slip by unnoticed, a pause between heartbeats in the rhythm of a day. But in the timeline of the universe, those same 3 minutes determine the chemistry of galaxies, the brightness of stars, and even the conditions that allow water, air, and life to exist. Everything since has been a long elaboration of what those moments established. If you could have watched the universe then, you wouldn't have seen anything resembling the night sky. There were no stars, no galaxies, no light escaping into space. Everything was dense, glowing and uniform, a cosmic fog lit from within. Yet hidden in that fog was the pattern of all that would come, the ratios of elements, the seeds of structure, and the faint murmur of photons that would one day become the cosmic background radiation. The universe was already quietly setting its long-term course, and so, the first 3 minutes passed, leaving behind a universe filled with hydrogen, helium, and traces of heavier elements. A recipe simple enough to describe on a blackboard, yet rich enough to build everything that exists. Those early reactions locked in the composition of the cosmos, providing a foundation stable enough to last for billions of years. You could say that, in those fleeting moments, the universe wrote its autobiography's first chapter, 3 minutes long, yet deep enough to contain eternity. For hundreds of thousands of years after the first elements formed, the universe was still a bright and restless fog. Everywhere you looked, light and matter were tangled together, bouncing and scattering in every direction. It was a universe without stars, without darkness, and without transparency. Photons couldn't travel more than a fraction of a millimeter before colliding with an electron. The cosmos glowed, but that glow couldn't escape. This was the plasma era, a time when the universe behaved like the interior of a star, filled with charged particles in constant motion. The main players were electrons, protons, helium nuclei, and photons. The photons, which are particles of light, had so much energy that they kept knocking electrons away from protons every time they tried to come together. The result was a universe that shimmered but never cleared, like a perpetual sunrise behind an infinite fog. But the universe was cooling, and with every expansion its temperature dropped just a little more. Slowly, imperceptibly, it approached a threshold where something remarkable could happen. When the temperature fell to around 3,000 degrees, roughly the heat of a glowing stove burner, the photons lost enough energy that they could no longer ionize hydrogen atoms. At that precise moment, electrons began to settle into stable orbits around protons. The cosmos underwent one of its most important transitions, recombination. Recombination sounds like a complicated laboratory process, but it's really just a poetic name for a simple idea. Electrons finally binding to nuclei to make atoms. For the first time, hydrogen and helium existed in their neutral atomic forms, and when that happened, everything changed. Freed from the constant scattering of electrons, photons could now move unhindered. Light could finally travel long distances without being absorbed. The universe, once an opaque plasma, became transparent almost overnight. That first flood of free light has been travelling ever since, stretching and cooling with the expansion of space, and it now fills the cosmos as the cosmic microwave background. It's strange but true. When you look at the CMB, you're not seeing stars or galaxies. You're seeing the universe itself as it looked when it became transparent, about 380,000 years after its beginning. Beyond that moment, light can't reach us directly. The universe before recombination is hidden behind a glowing curtain of radiation. In every direction, we are looking at the same cosmic surface of lost scattering, the final moment when photons were deflected by matter before streaming freely through space. You could think of it as standing inside a vast fog bank that suddenly clears. Before, you can't see more than a few feet. Afterward, your vision opens up all at once, revealing the landscape around you. The CMB is that moment of clarity, frozen in time and stretched across the entire sky. If you could have stood somewhere in the universe at that exact moment, though standing would have been tricky without solid ground, you would have seen a world bathed in warm orange-red light, glowing evenly in every direction. The temperature was around 3,000 degrees, similar to the surface of a cool star. That gentle radiance filled every corner of space, wrapping the newborn universe in a soft cosmic afterglow. Over billions of years, the expansion of space stretched that light into microwaves, cooling it to just 2.7 degrees above absolute zero, but it's still here, bathing everything in a quiet hum of radiation. During this transition, something else subtle but fascinating happened. The universe wasn't perfectly uniform. Tiny variations in density and temperature, seeded long before by quantum fluctuations and stretched during inflation, caused gentle pressure waves to ripple through the plasma. These sound waves, or acoustic oscillations, compressed and rarefied the gas, leaving behind patterns in the density of matter and radiation. When photons finally escaped, those patterns were imprinted in the light itself. Billions of years later, when satellites like WMAP and Planck mapped the CMB, scientists could still see those patterns. They appear as faint spots, slightly warmer or cooler by a few millionths of a degree. To the untrained eye, the CMB looks like abstract art, a dappled canvas of red and blue, but hidden in that texture are acoustic peaks, the frozen echoes of sound waves travelling through the early plasma. Each peak corresponds to a particular scale, like notes on a cosmic instrument, revealing how matter and radiation danced together before light broke free. By studying those peaks, scientists can deduce astonishing details: the density of matter, the curvature of space, and even the age of the universe. It's one of the most precise tools in all of science. And it began with the simple physics of sound waves rippling through a glowing fog. You could almost say the universe sang itself into clarity, and the CMB is the sheet music it left behind. Recombination didn't just make the universe transparent, it also marked the start of darkness. Once photons were free to travel, there were no more easy sources of light. The cosmos entered a long, dark age, filled with neutral hydrogen but devoid of stars. For hundreds of millions of years it would remain that way, a calm sea of invisible gas cooling under the silent pull of gravity. Only later, when the first stars ignited, would light return in a new form. But that's far ahead in the story. What's remarkable about this epoch is how final it feels. The light released at recombination defines the farthest we can ever see with our eyes or telescopes. No matter how advanced our instruments become, we can never peer back beyond this wall of light. Before recombination, the universe was opaque to radiation, so there's no direct information carried by photons from earlier times. Instead, we must infer what happened through particles like neutrinos or the faint imprint of gravitational waves. In that sense, the last scattering surface isn't just a milestone, it's the cosmic horizon of visibility. Yet even this limit has its beauty. Because the CMB comes from every direction, it creates a perfect sphere of light around us, centered wherever we happen to stand. Every observer, no matter where they are in the universe, sees their own last scattering surface at the same age. It's a gentle reminder that we're not looking outward into space so much as backward into time. When you gaze at the microwave background, you're seeing the universe's childhood portrait. Faint, ancient, and endlessly patient. The journey from plasma to transparency might sound like an abrupt shift, but it unfolded naturally, following the simple logic of cooling. The universe expanded, the temperature dropped, and once photons lost the energy to tear electrons from atoms, transparency was inevitable. What began as a dense fog gradually thinned into clarity. Every beam of light shining today, every sunrise, every star, is built on that foundation. The ability of light to travel freely is not just a detail of physics, it's the reason the cosmos is visible at all. And so, recombination stands as one of the great turning points in cosmic history, the moment when light and matter parted ways, each to follow its own path through time. The photons set off on their long journey across the universe, and the matter they left behind began to drift together, pulled by gravity toward its own destiny. In the faint microwave glow that still fills the night sky, we can read the echo of that moment, a whisper from when the universe first opened its eyes. When the universe first became transparent, it looked deceptively simple, just a vast, smooth sea of hydrogen and helium stretching in every direction. There were no galaxies yet, no stars, no clusters, just faint ripples in density left behind by the earliest fluctuations. And yet, hidden beneath that calm surface was a mysterious ingredient shaping everything to come. Dark matter. It doesn't glow, it doesn't reflect light, and it doesn't interact with ordinary atoms in any familiar way. But its gravity quietly choreographs the architecture of the cosmos. You can think of dark matter as the universe's invisible scaffolding. It doesn't shine, but it holds everything up. Without it, the ordinary matter that makes stars, planets, and people would never have had enough gravitational pull to form structures in time. Galaxies would have taken billions of years longer to assemble if they formed at all. The visible universe, the one painted in stars and light, is just the frosting. The real cake lies hidden underneath. Our awareness of dark matter began, fittingly, with things that didn't add up. In the 1930s, Swiss astronomer Fritz Zwicky studied the Coma Cluster, a collection of galaxies bound together by gravity. When he measured the galaxies' speeds, he found they were moving far too fast to be held by the visible mass alone. There had to be something else, some unseen matter, providing extra gravity to keep the cluster intact. Zwicky called it Dunkle Materie, German for dark matter, though few paid much attention at the time. Decades later, in the 1970s, American astronomer Vera Rubin gave the mystery a clearer shape. She studied how stars rotate around the centers of spiral galaxies, expecting that stars farther out would orbit more slowly, just as the outer planets in our solar system move more gently around the Sun. But instead of dropping off, the rotation curves flattened. Stars at the edges of galaxies were moving just as fast as those near the center, as if something unseen was providing extra gravitational glue. That something couldn't be normal matter. It didn't emit or absorb light. The simplest explanation was that galaxies sit within vast halos of dark matter, invisible but massive, extending far beyond the reach of their luminous arms. Since then, the evidence for dark matter has piled up like quiet but persistent proof. We see its fingerprints in gravitational lensing, the phenomenon predicted by Einstein where mass bends light. When we look at distant galaxies behind massive clusters, their light is distorted and magnified in arcs and rings. By mapping those distortions, scientists can calculate how much mass is doing the bending, and there's always far more than the visible matter accounts for. The lensing patterns reveal ghostly halos surrounding galaxies, shaping the paths of light without ever shining themselves. Then there's the cosmic microwave background, the universe's oldest light, frozen when it first became transparent. The tiny temperature ripples imprinted in that light carry information about how matter was distributed at that time. When scientists compare those ripples to computer models, the data fits beautifully only when dark matter is included. The peaks and valleys in the CMB's power spectrum, the cosmic fingerprint of those early sound waves, are shaped by both visible matter and an invisible counterpart that adds gravity but not light. Without dark matter, the pattern would look entirely different. Even the large-scale structure of the universe, the vast web of galaxies stretching across billions of light-years, bears dark matter's unmistakable influence. Astronomers using supercomputer simulations have recreated the cosmic web, feeding in the physics of gravity and expansion. The result is astonishing. The same filamentary patterns we see in real observations emerge naturally only when dark matter is included. These dark filaments formed first, their gravity pulling ordinary gas toward them like dust gathering along invisible beams. Over time, galaxies grew where the dark matter was densest, lighting up the skeleton of an otherwise invisible structure. The metaphor of scaffolding works beautifully here. Imagine building a city in the dark. You can't see the framework, but you notice that lights begin appearing in regular patterns. Streets, towers, clusters of windows. Those lights trace the hidden architecture holding them together. In the same way, galaxies are like glowing lanterns outlining an unseen framework of dark matter. We can't observe the scaffolding directly, but the pattern of light reveals where it must be. What then is this mysterious stuff? The short answer is that no one knows for sure. We know it interacts gravitationally, but not electromagnetically. It doesn't emit, absorb, or scatter light. It's not made of atoms or the particles that make up atoms. The leading idea is that dark matter consists of particles beyond the standard model of physics, perhaps something like weakly interacting massive particles, or WIMPs for short, though experiments searching for them have so far come up empty. Another possibility is that dark matter might be made of ultralight particles that act more like waves than billiard balls. There are even more exotic ideas, like primordial black holes formed in the earliest universe. The truth remains hidden, but every clue brings us closer. What we do know is that dark matter vastly outweighs ordinary matter. For every kilogram of visible atoms in the cosmos, there are roughly 5 kilograms of dark matter quietly shaping them. It dominates the gravitational landscape, dictating how galaxies form, how clusters assemble, and even how the universe expands. It is, quite literally, the invisible majority. Without dark matter, the timeline of structure formation wouldn't work. Ordinary matter interacts with radiation. It's pushed around by light, heated, cooled, and slowed. In the early universe, when photons were constantly colliding with electrons, regular matter was too tightly coupled to radiation to clump effectively. Dark matter, unaffected by light, could begin collapsing under its own gravity long before recombination. By the time the universe became transparent, dark matter had already formed dense halos and filaments. When the fog of plasma cleared, ordinary gas fell into those gravitational wells, where it condensed and cooled to form the first stars and galaxies. In a sense, dark matter set the stage, and visible matter merely followed its lead. It's easy to overlook something you can't see, but dark matter makes itself known through its quiet persistence. When astronomers measure how galaxies spin, how clusters bend light, or how the CMB ripples, the same invisible presence emerges again and again. Each piece of evidence is like a soft footprint in the sand, hinting at an unseen traveller who's been walking beside us since the beginning. The story of dark matter is one of humility. It reminds us that most of the universe is hidden from our senses. Our eyes, magnificent though they are, evolved to see only a tiny fraction of what's really there. The visible cosmos, the stars, the planets, the glowing nebulae, is just the shimmering surface of a much deeper reality. The rest moves in silence, shaping what we see but never revealing itself. Even now, experiments deep underground and high in orbit are trying to detect the faintest hint of dark matter directly. Physicists hope to catch a rare interaction, a tiny recoil in a detector that will confirm what the cosmos has been hinting at for decades. Whether that discovery comes soon or far in the future, the gravitational evidence is already overwhelming. The universe's behaviour simply makes no sense without this invisible mass guiding it. When you look up at the night sky, you're seeing the glittering lights of a city built on unseen beams. The galaxies trace a web you can't touch, but whose gravity you can feel in every cluster, every rotation, every arc of bent light. Dark matter may be invisible, but its fingerprints are everywhere, holding the cosmos together with silent grace. It's the hidden architect of creation, the quiet partner that never shines, yet makes all shining possible. For most of cosmic history, the universe's story seems simple enough. It began hot and dense, expanded rapidly, and then slowed as gravity tried to pull everything back together. Like a ball thrown upward, the expansion would rise, decelerate, and perhaps, if there were enough matter, fall back inward someday. For decades, that seemed the most reasonable ending, a universe that would eventually tire, halt, and collapse. But then, at the end of the 20th century, astronomers made a discovery so unexpected it flipped that story upside down. The universe wasn't slowing down, it was speeding up. The evidence came from the most dramatic beacons nature provides, exploding stars known as Type 1 supernovae. These are special because they all reach roughly the same intrinsic brightness when they erupt. That makes them perfect standard candles for measuring distances across billions of light years. By comparing how bright they appear to how bright we know they should be, astronomers can tell how far away they are. Combine that with how much their light is redshifted, how much the universe has expanded since the explosion, and you can trace the history of cosmic expansion itself. In the 1990s, 2 independent teams began gathering data from hundreds of these distant supernovae. They expected to see evidence that the universe's expansion was gradually slowing, tugged by gravity. But when the results came in, they showed the opposite. The distant supernovae were dimmer than expected, meaning they were farther away than they should have been if the universe's expansion were decelerating. The only explanation that fit was that the expansion was actually accelerating. Space wasn't just stretching, It was stretching faster and faster over time. This discovery was as shocking as it was beautiful. The cosmos, it seemed, wasn't content to drift gently outward. It was picking up speed. Some unknown force or energy was counteracting gravity on the larger scales, pushing galaxies apart as if the fabric of space itself were infused with repulsive pressure. That mysterious ingredient became known as dark energy. The term dark here doesn't mean it's sinister or even dark in colour. It simply means we don't know what it is. We can't see it, touch it, or measure it directly, yet its influence dominates the universe's fate. To visualize the cosmic inventory, imagine a pie chart representing the universe's total energy content. Ordinary matter, all the atoms that make up stars, planets, and living things, accounts for less than 5% of the total. Dark matter, that invisible scaffolding holding galaxies together, adds another 27% or so, and the remaining 68%, that's dark energy, filling space uniformly and driving the acceleration of expansion. It's humbling to realize that everything we can see, every speck of light and dust, is just a thin sliver of the cosmic budget. The vast majority of the universe is made of things we can't observe directly, and dark energy is the most dominant of all. It's the quiet ruler of cosmic destiny, shaping how the universe will evolve long after stars have burned out and galaxies have drifted beyond each other's reach. To understand what dark energy might be, scientists often describe it as a property of space itself. When Einstein first developed general relativity, he introduced a term called the cosmological constant, a sort of built-in energy of empty space, to keep the universe static. Later, when it became clear that the universe was expanding, he removed the term, calling it his greatest blunder. Yet it may not have been a blunder at all. If the vacuum of space naturally contains a small amount of energy, that energy would act like a gentle pressure pushing the universe apart, exactly as the supernova data suggest. But there are other possibilities. Dark energy might not be constant. It could evolve over time, driven by an unknown field that changes as the universe expands. Some models imagine a dynamic quintessence field that slowly alters the cosmic acceleration, while others propose modifications to gravity itself. Perhaps Einstein's equations need a subtle adjustment on the larger scales. Each idea has its own elegance, but none have yet been proven. What makes dark energy particularly fascinating is how it separates the early universe from the modern one. In the beginning, matter and radiation dominated everything. Gravity ruled, and expansion slowed down. Galaxies and clusters formed as matter clumped together under its pull. But as the universe expanded, the density of matter thinned out. Gravity's influence weakened, while dark energy, being tied to the fabric of space itself, remained constant or nearly so. Eventually, its repulsive effect began to dominate. Sometime about 5 billion years ago, the cosmic tug-of-war tipped in its favour. From that point onward, the expansion began accelerating, and the universe entered its current era of quiet speeding up. This distinction between the early and late universe is important. The Big Bang wasn't caused by dark energy. It was driven by the initial conditions of an incredibly hot, dense state. Dark energy is more like a late arrival, an effect that became significant only after billions of years. It doesn't ignite the beginning, it steers the future. To visualize the difference, imagine throwing a ball upward. Gravity slows it down as it rises, just as gravity initially slowed the universe's expansion. Now picture that ball suddenly gaining speed again, soaring higher and higher without anyone touching it. That's what happened to the cosmos when dark energy took over. The galaxies didn't start moving through space faster. Instead, the space between them began expanding more quickly. We can see the evidence of this acceleration in multiple independent ways. Beyond the supernova data, measurements of the cosmic microwave background show that the geometry of space is nearly flat. When combined with the amount of matter we observe, that flatness implies there must be an additional component, dark energy, to make up the difference. Observations of large-scale structure, including how galaxies cluster and how sound waves from the early universe, known as baryon acoustic, oscillations are imprinted in their distribution, all confirm the same conclusion. The universe's expansion is not only real but accelerating, and dark energy is the simplest explanation that ties it all together. Still, the nature of dark energy remains one of the great open questions in physics. Is it truly constant, a fixed property of the vacuum, or is it slowly changing? Could it decay someday, or even reverse its effect? No one knows yet. Experiments and telescopes are being designed to find out, including missions like the Euclid spacecraft and the Vera Rubin Observatory, which will map billions of galaxies to track how expansion has changed over time. Each new dataset helps tighten the constraints, narrowing the possible explanations. Whatever dark energy turns out to be, it has profound implications for the future. If its repulsive pressure remains constant, the universe will keep expanding forever, faster and faster. Galaxies not bound by gravity will drift beyond our observable horizon, their light redshifting into oblivion. Over unimaginable timescales, only the galaxies within our local group will remain visible, isolated in a growing sea of darkness. If, on the other hand, dark energy evolves or changes sign, the story could end differently, perhaps slowing again, perhaps collapsing, perhaps something stranger still. For now, we can say this much. Dark energy is real, measurable through its effects and deeply mysterious. It's a reminder that even in a universe built on equations and data, wonder still has room to roam. The same cosmos that once expanded from a hot, dense beginning now accelerates toward an uncertain future, powered by something we cannot see and barely understand. So when you look up at the night sky, you're not just seeing stars scattered through darkness. You're seeing a universe in motion, quietly picking up speed. The galaxies are coasting apart on a tide of invisible energy that fills every corner of space. It's as if the cosmos took a deep breath billions of years ago and never stopped exhaling. We may not yet know what drives that breath, but we can feel its rhythm in every widening gulf of starlight. And that, in its own strange way, might be the most beautiful mystery of all. When the universe first became transparent, it was astonishingly smooth, so uniform that if you could travel from one end to the other, you'd find almost the same temperature, the same density, the same tranquil glow wherever you went. But almost makes all the difference. Hidden within that near-perfect smoothness were tiny imperfections, minute ripples in density, just one part in 100,000 stronger or weaker than their surroundings. Those gentle wrinkles, stretched by inflation and frozen into the cosmic microwave background, were the seeds from which everything grew. Every star, galaxy, and cluster began as one of those faint ripples. Gravity, ever patient, went to work. Denser regions attracted more matter, pulling in gas and dark matter alike, while emptier regions gradually lost what little they had. Over millions of years, the dense spots grew denser and the voids grew emptier, a slow exaggeration of the universe's earliest imperfections. The process was unstoppable but subtle, like dew gathering into droplets on a window pane, or flour clumping together in a bowl of water. Those first overdensities were incredibly faint, but gravity had time on its side, and the universe had plenty of time to give. As the eons passed, the invisible dark matter did most of the heavy lifting. Unhindered by radiation, it collapsed into vast halos and filaments long before ordinary matter could join in. Gas followed the dark matter's gravitational pull, streaming toward the densest regions where it could cool and eventually ignite as stars. By the time the first galaxies appeared, they weren't scattered randomly through space. They were already tracing a larger hidden pattern, the cosmic web. If you could step back far enough to see the universe as a whole, really far across billions of light years, you wouldn't see galaxies sprinkled evenly like glitter on black paper. You'd see filaments and knots forming a three-dimensional lattice, woven together like strands of luminous silk. Between them, enormous empty voids stretch across the cosmos, dark bubbles surrounded by walls of clustered light. It looks uncannily like the foam on the surface of water, or the pores in a sponge, or the delicate network of neurons in a brain. This is the large-scale structure of the universe, a cosmic web shaped by gravity and time. Astronomers first caught glimpses of this pattern in the late 20th century. When galaxy redshift surveys began mapping the positions of hundreds of thousands of galaxies, the data revealed that they were not randomly distributed at all. They formed chains, walls, and clusters separated by great cosmic deserts. The discovery was breathtaking. What had once seemed like scattered dots on a sky map suddenly came into focus as part of a grand structure. Today, those maps have become astonishingly detailed. The Sloan Digital Sky Survey, for example, has charted millions of galaxies across billions of light years, showing us a universe that resembles a lacework of glowing threads. And yet those observations match almost perfectly with what computer simulations predict. Using the laws of physics, gravity, expansion, and the known amounts of dark matter and dark energy, scientists can run cosmic simulations that start from the faint ripples measured in the cosmic microwave background. As the virtual universe evolves, it naturally grows into the same filamentary pattern we see in real data. The fact that the two line up so closely is one of the great triumphs of modern cosmology. In those simulations, dark matter behaves like a kind of invisible glue, flowing into long filaments that intersect at dense nodes. These intersections become the cradles of galaxy clusters, massive collections of hundreds or even thousands of galaxies bound together by gravity. Along the filaments themselves, smaller galaxies form like beads on a cosmic string. Meanwhile, the empty regions between them expand, becoming vast voids where few galaxies reside. The contrast between the crowded filaments and the lonely voids gives the universe its spongy texture. But why does the cosmos prefer filaments and clusters instead of forming a smooth gradient or random scatter? The answer lies in how gravity amplifies tiny differences. In regions where matter was slightly denser, its gravity drew in material from nearby space, causing those areas to collapse along specific directions, first into thin sheets, then into filaments, and finally into knots. This process is known as anisotropic collapse, and it's the natural outcome of gravity acting in 3 dimensions. Instead of everything falling inward uniformly, matter streams along the paths of least resistance, forming long, thread-like rivers that feed into galaxy clusters. The result is a universe sculpted by geometry and motion, not chaos. Inside these filaments, galaxies don't just sit passively, they interact, collide, and merge. Smaller galaxies fall into larger ones, growing them over time. In dense clusters, their motions are so fast that collisions are common, triggering bursts of star formation or, in some cases, stripping galaxies of gas entirely, leaving them dormant and red. The cosmic web is not a static structure but a dynamic ecosystem, constantly evolving under the pull of gravity and the gentle push of cosmic expansion. What's especially striking is how well this cosmic architecture mirrors the physics of sound in the early universe. The same ripples that shaped the cosmic microwave background, the acoustic waves propagating through the hot plasma, set the stage for where galaxies would later form. The peaks and troughs of those waves defined where matter was slightly denser, and over billions of years those regions became the filaments and clusters we see today. The pattern is, in a sense, the frozen music of the Big Bang, harmonic ripples turned into the scaffolding of the cosmos. Even now, astronomers use the large-scale structure as a cosmic yardstick. The characteristic spacing between clusters, about 500 million light-years, carries the imprint of those primordial sound waves known as baryon acoustic oscillations. By measuring that scale at different times in cosmic history, scientists can track how the universe's expansion has changed, providing crucial clues about dark energy. The structure of the universe isn't just beautiful, it's also a living record of its entire evolution. If the cosmic web could somehow be lit from within, it would glow like a faint ghostly network stretching endlessly in all directions. Galaxies would gleam along its strands, clusters would sparkle at the intersections, and dark matter, still invisible, would quietly outline the shape of it all. It's a pattern both intricate and serene, the universe's own fingerprint repeated on every scale. From the smallest groups of galaxies to the largest superclusters, the same geometry persists, echoing the same cosmic rhythm. Every night, when you look up at the stars, you're seeing only the brightest jewels on that immense web. Our Milky Way is just one node, connected by unseen filaments to galaxies millions of light-years away. Through gravity's patient work, those connections will continue to evolve, even as dark energy gently stretches the fabric of space. The web will grow thinner, the filaments will drift apart, but the pattern itself will endure for billions of years, a frozen trace of the universe's formative dance. The transformation from ripples to webs is one of nature's most astonishing achievements. It's the story of how the smallest quantum fluctuations became the grandest structures imaginable. From near-perfect uniformity emerged infinite variety. From simplicity, elegance. The next time you imagine the universe, don't picture it as a void with scattered stars. Picture a sponge of light, a delicate glowing foam where galaxies shimmer like dew on invisible threads. That is the true shape of everything, a cosmic tapestry woven by gravity, time, and the quiet hum of the expanding universe. Before there were galaxies with spiral arms, before there were planets or even dust, the universe was dark and quiet. For hundreds of millions of years after recombination, the cosmos drifted through what astronomers poetically call the cosmic dark ages. The light from the Big Bang had faded into the microwave background, and no new sources of light had yet appeared. Space was filled with cold hydrogen and helium gas, slowly gathering under the pull of gravity. The universe was waiting for something to spark, the first candles that would turn the darkness into dawn. Those first stars, called Population 3 stars, were unlike anything that shines today. They were the pioneers of starlight, the first objects to ignite nuclear fusion and pierce the cosmic night. In a universe made purely of hydrogen, helium, and traces of lithium, they had no heavier elements, no carbon, oxygen, or iron, to help cool the gas or form complex molecules. Astronomers call these heavier elements metals, and though the term might sound odd, it simply means everything heavier than helium. Because Population 3 stars formed in a metal-free environment, they behaved very differently from later generations. Without metals to radiate heat away, the gas clouds that formed the first stars couldn't fragment easily into small clumps. Instead, they collapsed into a few enormous ones. Simulations suggest that these stars were monsters, perhaps 100, 200, or even several hundred times more massive than our Sun. They burned hotter, lived shorter, and shone brighter than almost anything since. Some may have lived only a few million years, a cosmic heartbeat compared to the Sun's expected lifespan of about 10 billion. Yet in that brief time they transformed the universe forever. When those first stars ignited, the universe went from dark to dazzling. Their ultraviolet light began to break apart the surrounding hydrogen atoms, ionizing the gas that had filled space since recombination. This process, known as reionization, gradually turned the opaque universe transparent once more. The first starlight didn't just illuminate the cosmos, it changed its chemistry and structure. The intergalactic medium, once neutral and cool, became warm and electrically charged again. It was as if the cosmos had flicked the lights back on after a long slumber. These early stars also forged the first new elements. In their cores, nuclear fusion turned hydrogen into helium, and helium into heavier nuclei, carbon, oxygen, nitrogen, and beyond. When they died, many of them ended in spectacular explosions called pair instability supernovae, scattering those newly minted elements into the surrounding gas. Others collapsed directly into black holes, perhaps seeding the supermassive black holes that now sit at the centres of galaxies. Either way, the universe's chemical monotony was broken. The ashes of those first stars became the raw material for everything that followed. Second-generation stars, planets, and eventually life itself. Every atom of carbon in your body, every bit of oxygen you breathe, every iron atom in your blood was once fused in the heart of a star, and the very first of those atoms came from population 3. They were the universe's original alchemists, turning the simplest ingredients into the complex chemistry that makes biology possible. Yet for all their importance, these first stars remain elusive. No telescope has ever seen one directly. They lived and died in the farthest reaches of time, so distant that their light has been stretched into infrared wavelengths by the expansion of the universe. By now, even that light has faded beyond our reach. What we know about them comes from simulations, theory, and indirect clues left behind in later generations of stars. Astronomers search for their fingerprints in the oldest, most primitive stars still shining today. These ancient stars found in the outskirts of our galaxy and in dwarf galaxies nearby contain extraordinarily low amounts of heavy elements. They act like time capsules, preserving the chemical traces of the first supernova. By studying their compositions, scientists can infer how massive the first stars were and what kinds of explosions they produced. Some of these ancient survivors may even have formed from gas enriched by just one population 3 supernova, a faint whisper of the universe's first fireworks. New telescopes have joined the hunt. The James Webb Space Telescope, with its infrared eyes, is designed to peer deeper into the cosmic past than ever before. It can detect galaxies that existed only a few 100 million years after the Big Bang, perhaps catching the afterglow of the first stellar generations. Though Webb can't resolve individual population 3 stars, it can reveal their collective influence, the way they brightened the universe and shaped the early galaxies that followed. If we're lucky, we may someday witness a signature spectrum that could only come from stars with no metals, marking the moment when the cosmos first learned to shine. The challenge of finding them adds to their mystique. Even with our best instruments, the first stars remain ghosts, too faint, too far, too brief to be seen directly. Yet their presence is undeniable, written in every galaxy, every atom heavier than helium, every glimmer of starlight since. It's one of those rare scientific stories that feels almost mythic, invisible heroes who built the foundations of everything. It's also fascinating to think about how different their light must have been. With such enormous masses, these stars burned at tremendous temperatures, pouring out ultraviolet radiation that sculpted the early universe. Some of the most massive may have ended their lives as direct collapse black holes, so heavy that they could swallow nearby matter and grow rapidly. These may be the ancestors of the supermassive black holes we see today at the centres of galaxies, already surprisingly large just a few 100 million years after the beginning. The seeds of those cosmic giants might trace back to the brief, blazing lives of population 3 stars. In a sense, these first stars played the role of cosmic gardeners. They took a simple, unvaried landscape and planted diversity into it. Their explosions enriched the interstellar medium with the elements needed for rocky planets, oceans, and even DNA. Each new generation of stars that followed contained a little more metal, a little more complexity, until the universe began to sparkle with colour and variety. The golden hues of sun-like stars, the red glows of cool dwarfs, the heavy elements in distant nebulae, all are echoes of the first generation's legacy. There's a quiet poetry in the idea that the first stars shone and vanished before anything could see them. They lit up a universe that had no eyes to witness it, no worlds to feel their warmth, no beings to marvel at their light, and yet their brilliance was not wasted. Every sunrise, every glittering night sky, every element that makes life possible is a continuation of what they began. If you could stand somewhere in that young universe, impossible though that would be, you'd see the first stars ignite against a backdrop of deep cosmic night. Their light would be bluer and more intense than anything our eyes could bear. Around them, the once cold hydrogen gas would glow as it reionized, transforming the universe from dark to luminous. In time, the glow would spread, merging into a cosmic dawn that marked the end of the Dark Ages. Those first lights didn't last long, but they changed everything. From them came the chemistry of worlds, the fuel for future stars and the seeds of life itself. Their light still echoes through the cosmos, not as visible starlight, but as the presence of everything they left behind. The universe's first candles may have burned quickly, but in doing so, they illuminated the path for everything that followed. After the first stars burst into life, the universe entered one of its most transformative eras. The long darkness that had followed the Big Bang began to lift, and the cosmos slowly emerged from its youthful haze. Tiny galaxies, mere dwarf systems of stars and gas, began to appear, scattered like glowing embers across a vast and murky expanse. Over hundreds of millions of years, those small structures collided, merged, and evolved into the grand galaxies we see today, from majestic spirals like the Milky Way to massive ellipticals that house trillions of stars. The story of galaxies is one of endless assembly. The first ones were fragile and chaotic, small collections of gas and dark matter bound together by gravity. They lacked the symmetry and order of modern galaxies, more like turbulent clouds than stable islands of stars. As time passed, gravity stitched these dwarfs together. Each collision brought new material, new bursts of star formation, and new possibilities. The process wasn't gentle, it was cosmic construction by collision. When galaxies met, their stars often passed by unharmed, but their gas clouds crashed and compressed, sparking new generations of stars. Over time, these mergers sculpted the familiar shapes we know: graceful disks, elegant spirals, and dense central bulges. Inside these growing galaxies, stars were living fast and dying young. The first generations of massive stars released torrents of radiation and powerful winds, pushing against the gas that surrounded them. When those stars exploded as supernovae, they hurled heavy elements into space and stirred the interstellar medium like spoons in a cosmic soup. This feedback, the pushback of light, wind, and shock waves, played a crucial role. It prevented galaxies from forming too many stars too quickly, helping them evolve in balance. Without feedback, early galaxies would have burned through their gas in a single frenzied burst, leaving little behind for future generations. As these processes continued, galaxies developed distinct personalities. Some spun into flattened disks, where gas settled into orderly rotation, forming spiral arms. Others, shaped by more violent encounters, became irregular or elliptical. By around 1 billion years after the beginning, galaxies were no longer mere blobs of light. They were structured, dynamic systems, already tracing the grand designs that would define cosmic history. But the light of these newborn galaxies had a much larger job to do. The early universe was still shrouded in a faint fog of neutral hydrogen gas. This fog absorbed ultraviolet light, making the cosmos effectively opaque beyond local regions. It was a second veil, different from the plasma fog that had cleared during recombination but equally important. To make the universe transparent again, that hydrogen needed to be ionized, stripped of its electrons. The process began with the first stars and galaxies, whose energetic photons started punching holes in the neutral gas. This grand transition is known as the era of reionization, and it marks the universe's second clearing of fog. It unfolded over several 100 million years, beginning when the first sources of light appeared and ending when the intergalactic medium was almost entirely ionized. In simple terms, it was the moment when light reclaimed the universe. Picture it as a slow sunrise on a cosmic scale. In the beginning, isolated pockets of ionized gas formed around young galaxies, tiny bubbles of clarity in an otherwise dark sea. As more galaxies ignited, those bubbles grew and merged, overlapping until the entire cosmos was transparent once again. By about 1 billion years after the Big Bang, the fog had lifted completely, and starlight could travel freely across space. This transformation wasn't uniform or instantaneous. Some regions reionized earlier than others, depending on where galaxies formed more densely. The process was patchy, with bright spots of cleared space expanding through the darkness like lanterns lighting up a field at night. Astronomers have long wanted to pinpoint exactly when and how this cosmic dawn unfolded, and to do that, they've had to rely on clever techniques, since the light from that era is faint and redshifted far into the infrared and radio bands. One of the most valuable clues comes from quasars, the brilliant supermassive black holes at the centres of young galaxies. Quasars are so luminous that their light can travel across billions of light years, illuminating the gas between galaxies along the way. When astronomers study the spectra of distant quasars, they can see how much of that light has been absorbed by hydrogen gas on its journey. The presence of a Gunn-Peterson trough, a deep absorption feature caused by neutral hydrogen, tells scientists how much of the universe was still opaque at different times. Quasar observations have shown that by roughly 1 billion years after the beginning, the fog of hydrogen had mostly cleared, giving us a timestamp for the end of reionization. Another subtler clue comes from the faint radio glow of hydrogen itself. Neutral hydrogen naturally emits radiation at a wavelength of 21 centimeters, and this signal offers a unique way to map the universe before and during reionization. As galaxies lit up and began ionizing their surroundings, the 21 centimeter signal weakened in those regions, creating a patchwork of bright and dark areas that trace the spread of ionized bubbles. Modern radio telescopes, like the Hydrogen Epoch of Reionization Array in South Africa and the Square Kilometre Array now under construction, are designed to detect this signal, effectively letting scientists watch the universe's dawn unfold. It's one of the most challenging observational goals in all of astronomy, but it promises to fill in the final missing chapters of how light reclaimed the cosmos. Reionization also played a defining role in shaping the galaxies themselves. As ultraviolet light from early stars and quasars ionized the surrounding gas, it heated the intergalactic medium, making it harder for smaller galaxies to pull in fresh material. That feedback throttled star formation in the tiniest systems and helped explain why we see fewer small galaxies today than early models once predicted. In this way, the growth of galaxies and the reionization of the universe were intertwined, each influencing the other in a complex cosmic dialogue. What makes this period so enchanting is how much of it remains hidden from view. The galaxies responsible for reionization were faint and far away, barely visible even with the most powerful telescopes, yet their collective light transformed everything. The James Webb Space Telescope has already glimpsed some of the earliest galaxies known, shining when the universe was less than 400 million years old. Their brightness and abundance suggest that star formation was already well underway, perhaps earlier than expected. Every new observation adds a piece to the puzzle, refining our picture of how the first cosmic dawn spread across the sky. In a way, the era of reionization is the moment when the universe took a deep breath and opened its eyes. The Dark Ages ended, the fog lifted, and the cosmos began to sparkle. The galaxies that formed during this time were not just islands of stars, they were engines of transformation, reshaping their surroundings with light and heat. If you could witness that epoch firsthand, you'd see a universe alive with contrasts. Pockets of blazing starlight would glow within a backdrop of cool, neutral gas. Expanding bubbles of ionized hydrogen would merge like rising soap bubbles, turning the night into a mosaic of light and shadow. Over millions of years, the darkness would fade entirely, replaced by the luminous weave of galaxies tracing the cosmic web. By the end of reionization, the universe looked much more familiar, transparent, filled with galaxies, and governed by the same physical laws that persist today. The cosmic dawn had given way to day. From that point onward, light would travel freely, carrying the stories of stars, galaxies, and life itself. And though those first galaxies are long gone, their light, stretched thin and red by the passage of time, still drifts through the cosmos, whispering of the morning when the universe learned to shine. Among the many relics of the early universe, the ancient light of the cosmic microwave background, the primordial hydrogen and helium, the vast web of galaxies, there's another remnant that almost never gets invited to the conversation. It's faint, elusive, and famously shy. Cosmologists call it the cosmic neutrino background, a bath of ghostly particles that's been drifting through the universe since long before light could even move freely. If the cosmic microwave background is the baby picture of the visible universe, the neutrino background is the ultrasound image from before it was born. Neutrinos are the introverts of the particle world. They hardly interact with anything at all, quietly passing through stars, planets, and people without so much as a polite hello. Every second, trillions of them stream through your body and you don't feel a thing. They don't carry charge, they barely have mass, and they're immune to the electromagnetic force. In fact, neutrinos are so indifferent to their surroundings that they can travel through light years of solid lead without stopping. If particles had personalities, neutrinos would be the ones standing in the corner of the cosmic party, sipping something invisible, hoping no one notices them. Yet for all their social awkwardness, neutrinos have been part of the universe's story from the very beginning. In the first few seconds after the Big Bang, when the cosmos was a dense plasma of particles and radiation, neutrinos were everywhere, colliding and exchanging energy like everyone else. But as the universe expanded and cooled, the interactions slowed down. About 1 second after the beginning, the neutrinos decoupled. They stopped bumping into other particles and began streaming freely through space. From that moment on, they'd been travelling in straight lines, barely affected by anything that came afterward. while photons had to wait almost 400,000 years for the universe to become transparent. Neutrinos were already off exploring. This makes the cosmic neutrino background the oldest fossil we have, a snapshot of the universe from a time even earlier than the release of the cosmic microwave background. While we can't see it directly, it's everywhere. A quiet ocean of particles left over from that first second. Every cubic centimetre of space contains hundreds of relic neutrinos, each carrying a whisper of information about the earliest conditions of the cosmos. So why can't we detect them easily? Because they are, quite literally, too aloof. Their interactions with matter are so weak that no existing detector can pick up the cosmic neutrino background directly. The neutrinos we can detect, those produced in the Sun, in nuclear reactors or in supernovae, are billions of times more energetic than the ancient relics from the Big Bang. The cosmic ones have cooled to a temperature of just under 2 degrees above absolute zero, making them slower and even more ghostly than their younger cousins. They drift through space like invisible snowflakes, unbothered by stars, galaxies, or detectors. Still, scientists know they exist, not because they've seen them directly, but because the universe behaves as if they're there. The fingerprints of neutrinos are subtly woven into the cosmic microwave background and the large-scale structure of galaxies. When cosmologists model the evolution of the universe, they find that they can only get the right answers, matching the observed temperature fluctuations in the CMB and the distribution of matter, if neutrinos are included. It's as if the universe insists on acknowledging their presence, even though they refuse to show up for photographs. The influence of neutrinos begins with their sheer abundance. Even though each one carries only a tiny amount of energy, there are so many of them that together they make a noticeable contribution to the universe's energy density. In the early universe, this meant that neutrinos played a key role in how fast the cosmos expanded. More neutrinos meant more energy, and more energy meant a faster expansion rate. That, in turn, influenced how matter clumped together and how light moved through the primordial plasma. The result is that the cosmic microwave background still carries subtle imprints of the neutrino population that existed when it was released. One of the ways this shows up is in the damping of small-scale fluctuations in the CMB. Because neutrinos move so quickly, nearly at the speed of light, they tend to smooth out density variations as they stream across space. They act like a kind of cosmic anti-clumping agent, ironing out some of the smaller wrinkles in the fabric of matter. This subtle smoothing effect helps cosmologists count how many neutrino species there are and even estimate their combined mass. It's astonishing that by studying faint variations in ancient light, we can infer properties of particles that barely interact with anything at all. As the universe evolved, neutrinos continued to shape its structure, though always quietly from the sidelines. When matter began to gather into galaxies and clusters, neutrinos resisted falling into those gravitational wells. Their lightness made them fast-moving, and their speed prevented them from staying put long enough to contribute much to the formation of structures on small scales. In this way, neutrinos acted as a kind of cosmic brake, slightly slowing down the growth of galaxies. Without them, the universe would look subtly different. Galaxies might have formed sooner and clusters might have grown denser. Even today, neutrinos remain one of the few windows into physics beyond what we currently understand. For decades, scientists assumed they were completely massless, but experiments in the late 20th century revealed that they do in fact have tiny masses. So tiny that it took observing how they oscillate between different flavours to prove it. That discovery alone was enough to confirm that our standard model of particle physics is incomplete, and while we know they have mass, we still don't know exactly how much. Measuring that number is one of the great goals of modern cosmology, because the total mass of neutrinos subtly influences how structure forms across the cosmos. The heavier they are, the more they damp small-scale clustering. By comparing precise maps of the cosmic web to theoretical predictions, scientists can narrow down that mass range. An extraordinary way to weigh particles that we can't even see. It's poetic, really, that something so intangible has had such a lasting effect on everything. Neutrinos don't shine, they don't bind, and they barely talk to other particles, yet they helped decide how galaxies arrange themselves across billions of light years. They are the quiet custodians of cosmic structure, influencing outcomes without ever taking the spotlight. Some physicists like to joke that neutrinos are the universe's version of background music, always playing, rarely noticed, but impossible to remove without changing the whole experience. If you could somehow turn them off, the universe would feel just slightly wrong. The galaxies wouldn't line up quite the same way. The cosmic microwave background would hum a different tune. The rhythm of creation itself would shift. The search for the cosmic neutrino background continues, though it requires incredible sensitivity. Future experiments may someday catch its whisper, perhaps by observing how these relic neutrinos affect certain nuclear decays or how they influence the motion of massive objects. For now, their existence is confirmed indirectly, and their legacy is written in the fabric of space itself. It's easy to think of neutrinos as an afterthought, a technical detail in the equations of cosmology, but in truth, they're proof of how deeply interconnected everything in the universe really is. Even the most elusive, nearly massless particles have left measurable fingerprints on the grandest scales imaginable. They remind us that cosmic history isn't written only by the bright and the loud. Sometimes it's the quietest voices that carry the deepest truths. So, while photons from the cosmic microwave background get all the attention, posing for our telescopes and painting the universe's first portrait, the neutrinos were there first, silently setting the tempo. They're the subtle percussion beneath the symphony of creation, the background hum that keeps time as galaxies dance and light drifts through space. Introverts they may be, but without them, the universe's music would be missing its rhythm. At first glance, the universe seems to love symmetry. From the way galaxies spin to the laws that govern particles, nature tends to favour balance and elegance. But there's one glaring exception to that rule, one tiny imbalance without which nothing, no stars, no planets, no life could exist. It's the puzzle of matter and antimatter, the cosmic coin flip that somehow landed on something instead of nothing. According to everything we know about physics, the Big Bang should have created matter and antimatter in equal amounts. For every proton, an antiproton, for every electron, a positron. Matter and antimatter are identical twins in every respect except for their electric charge, and when they meet they annihilate one another, converting completely into energy. It's a spectacular process, 100% efficient, no waste, no leftovers, just pure light. But look around. You, your screen, the stars overhead, the entire visible universe, everything you can see, is made of matter. Antimatter, meanwhile, is practically non-existent. We can produce small quantities in laboratories and high-energy collisions, but the cosmos isn't full of antimatter galaxies mirroring our own. If matter and antimatter had truly been created in equal numbers, they would have annihilated each other almost instantly, leaving behind nothing but radiation. The universe would be a featureless sea of photons, devoid of atoms, chemistry, and the long story that followed. So how did matter win? Somehow, in those first moments after the Big Bang, the laws of nature allowed a tiny bias, roughly one extra matter particle for every billion matter-antimatter pairs. That sliver of imbalance was enough. As the universe cooled, the pairs destroyed each other in great flashes of gamma radiation, and the leftover 1 in a billion particles of matter became everything. That minuscule asymmetry decided the fate of the cosmos. This great question, Why the universe contains matter at all is one of the deepest mysteries in modern physics. The problem isn't that we have no clues. In fact, back in 1967, Soviet physicist Andrei Sakharov laid out 3 basic conditions that any explanation must satisfy. They're simple to state, even if they're tricky to achieve. First, the laws of physics must allow processes that treat matter and antimatter differently. In technical terms, this means there must be a violation of CP symmetry, where C stands for charge and P for parity, or mirror symmetry. Essentially, the universe must prefer one side of the coin just slightly more than the other. Second, there must be interactions that allow baryon number, the count of particles like protons and neutrons, to change. If you can't create more matter than antimatter, you can't build an imbalance. And third, these processes must occur out of thermal equilibrium. When the universe is in perfect balance, reactions create and destroy particles at the same rate, erasing any asymmetry that appears. You need a bit of disequilibrium, a moment when the cosmic kitchen is heating unevenly, for the recipe to come out lopsided. Sakharov's framework was like a roadmap. It didn't say how the imbalance happened, but it told physicists what ingredients were required. Since then, generations of scientists have tried to fill in the details. One promising approach lies within the standard model of particle physics itself. We know that CP symmetry can be violated. It's been observed in certain decays of subatomic particles called kaons and B-mesons. These tiny deviations show that nature does in fact distinguish between matter and antimatter, just not strongly enough to explain the vast imbalance we see. The known sources of CP violation within the standard model fall short by many orders of magnitude. It's as though the recipe calls for a cup of asymmetry, and we can only find a teaspoon. Something else must have happened. One candidate mechanism is known as leptogenesis, which shifts the spotlight from protons and neutrons to neutrinos. In this scenario, the early universe may have contained heavy, unstable neutrinos that decayed in a way that slightly favoured matter over antimatter. Their decay products could then have triggered the chain of events leading to the matter-dominated universe we know. The beauty of this idea is that it connects 2 mysteries, the origin of matter and the mass of neutrinos, into one elegant story. It's still hypothetical, but ongoing experiments in neutrino physics may someday reveal whether nature chose this path. Another possibility involves physics beyond the standard model altogether. Theories like supersymmetry, grand unification, or interactions involving new particles could provide the necessary asymmetry. These ideas are bold, sometimes speculative, but that's the fun of it. The puzzle is so fundamental that even a small clue could rewrite our understanding of the universe's first moments. It's also possible that the imbalance arose during a phase transition, one of the many cooling events, as the universe expanded and its fundamental forces separated. Imagine the cosmos as a pot of water cooling into ice, with bubbles of one phase forming within another. If matter and antimatter behave slightly differently during such a transition, a small excess of matter might have emerged. Some physicists call this baryogenesis, and it remains one of the leading fields of theoretical research. Despite decades of progress, the mystery remains unsolved. We can measure the result, the overwhelming dominance of matter, but not yet the mechanism. It's a bit like finding yourself in a room filled with cookies and trying to figure out who baked them when the recipe book is missing. We can guess from the crumbs, but the chef's hand is long gone. What's striking is just how delicate the whole situation is. If the asymmetry had been smaller, there would have been no galaxies, no stars, no life. If it had been larger, the early universe would have been cluttered with matter, changing its expansion history and the formation of structures. The cosmic balance landed in a narrow, perfect window, enough matter to build a universe, but not so much that it collapsed under its own weight. It's as though the universe flipped a coin and it landed on edge. This raises profound questions. Is that balance just chance? a random quantum fluctuation magnified by the early conditions? Or does it reveal something deeper, some hidden rule in the laws of physics that tips the scales ever so slightly toward creation over destruction? Physicists continue to search for that answer in every particle collision and cosmic signal, hoping to glimpse the mechanism that broke the symmetry of nothingness. Even though we don't yet know the how, we can still appreciate the what. Every atom, every breath of air, every glowing star is a monument to that tiny preference the universe once expressed. It's a reminder that imperfection can be powerful, that without a slight imbalance there would be nothing at all. And perhaps there's something poetic in the fact that matter's victory wasn't loud or dramatic. It wasn't an explosion or a grand event. It was a whisper, a 1 in a billion tilt in the rules of nature. That whisper gave rise to galaxies, planets, and all the wonders that followed. So next time you hold something solid in your hands, think about how unlikely it is. The universe could just as easily have chosen balance and left behind nothing but light. Instead, it leaned ever so slightly toward matter, and here we are, the improbable result of a cosmic coin flip that came up something. Measuring the universe is a little like trying to weigh an elephant using only its shadow. You can't grasp the whole thing directly, so you learn to use indirect clues, patterns, distances, and the way light bends or dims to piece together the bigger picture. What's remarkable is that despite the enormity of the challenge, we've managed to turn faint smudges of light on the sky into precise numbers that describe the entire cosmos. We know how fast it's expanding, how old it is, what it's made of, and even how it will likely evolve. But none of that knowledge rests on a single measurement. It comes from a chorus of independent methods all agreeing on the same tune. The universe, in its generosity, gives us several rulers we can use to measure it. Each one comes from a different physical process, yet they all tell the same story. One of the most elegant of these rulers is the Baryon Acoustic Oscillation, or BAO for short. That mouthful of a name describes the frozen imprint of sound waves that rippled through the hot plasma of the early universe. Before recombination, matter and radiation were tightly coupled, and sound waves propagated through the dense gas like ripples in water. When the universe cooled enough for atoms to form, those waves froze in place, leaving behind a preferred scale, a subtle tendency for galaxies to be separated by about 500 million light-years. By measuring that spacing in the distribution of galaxies today, astronomers can infer how the universe has expanded since those ancient ripples were set. The BAO signal acts like a cosmic yardstick, telling us how distances stretch with time. Another invaluable tool is gravitational lensing. Einstein's general relativity predicts that mass bends light, and the universe obliges beautifully. When light from distant galaxies passes near massive clusters, or even concentrations of dark matter, its path is warped, producing arcs, distortions, or magnifications. By studying these distortions, how much and in what pattern, astronomers can map the distribution of mass, both visible and invisible. Lensing serves as a natural telescope, magnifying distant galaxies, but it's also a way to measure the universe's geometry and growth of structure. The more matter there is and the faster it's clumping, the stronger the lensing effects. Galaxy clusters themselves are another important probe. They are the largest gravitationally bound structures in the universe, each one containing thousands of galaxies, oceans of hot gas, and enormous halos of dark matter. The number of clusters we see at different distances tells us about the balance between gravity, which tries to pull matter together, and dark energy, which drives the expansion apart. The cluster population acts like a cosmic census, reflecting how quickly structure has formed over billions of years. And then, of course, there are the type Ia supernovae. the same standard candles that first revealed the accelerating expansion of the universe. Because these supernovae all reach nearly the same intrinsic brightness, they provide a consistent way to measure cosmic distances. When astronomers plot their apparent brightness against redshift, they get a map of how space has stretched over time. Combined with the other methods, they allow us to trace the universe's entire expansion history with impressive accuracy. Each of these techniques, BAO, lensing, clusters, supernovae, tells us something slightly different. And that's the point. Science builds confidence not through repetition, but through convergence. When completely different observations based on unrelated physics all point to the same set of cosmic parameters, we know we're onto something real. It's like having several musicians play the same melody on different instruments. If it sounds harmonious, the tune is probably right. But how do astronomers turn this symphony of data into actual numbers? It's not done through one dramatic aha moment, but through a process of careful fitting and cross-checking. Imagine the universe as a recipe, with a few key ingredients: the rate of expansion, the Hubble constant, the density of dark matter and dark energy, the curvature of space, and the age since the Big Bang. Each observation we make, the CMB, galaxy surveys, or supernovae, constrains some of those ingredients but not all of them. By comparing how each dataset overlaps with the others, cosmologists can narrow down the exact amounts. In practice, this means using sophisticated models to simulate what the universe would look like for different combinations of parameters. Those models produce synthetic sky maps, which are then compared to real observations. The goal is to find the set of parameters that makes the simulated universe match the real one as closely as possible. When you hear cosmologists say that the universe is 13.8 billion years old, or that dark energy makes up about 68% of the total energy budget, those numbers come from this process of iterative refinement. It's a bit like adjusting a recipe by taste. One observation tells you there's too much salt, another hints that there's not enough sugar. Gradually you tweak the ingredients until everything fits, and when completely different recipes, each based on distinct physics, end up producing the same flavour, you can be confident you found the right mix. One of the great triumphs of this approach was the Planck satellite's detailed mapping of the cosmic microwave background. By analysing the temperature fluctuations in that ancient light, scientists extracted precise values for key cosmological parameters. Those values, when compared with independent measurements from galaxy surveys, supernovae and BAO, lined up beautifully. The result was a model of the universe so consistent it earned its own nickname, the Standard Cosmological Model, or Lambda CDM. It's not a perfect theory, no theory ever is, but it describes the data with astonishing precision across a vast range of scales. Of course, there are still small tensions, like the ongoing debate about the exact value of the Hubble constant, where different methods produce slightly different results. Some see these discrepancies as hints of new physics, while others suspect subtle measurement issues. Either way, the process of cross-checking remains the cornerstone of progress. The fact that most methods agree so closely is remarkable. The fact that a few don't keep science interesting. One of the most beautiful things about cosmology is how it unites the very large and the very small. The expansion of the universe, the behaviour of dark energy, the masses of neutrinos, even the curvature of space. All these can be constrained by studying light from ancient stars and galaxies. Each photon that reaches us carries a message about its journey, and by collecting enough of them, we can reconstruct the story of the cosmos with astonishing clarity. If you imagine the universe as a vast stage, our measurements are the footprints left behind by its performers. BAO marks the rhythm of the earlier sound waves. Lensing shows the graceful bends of light as it passes through massive structures. Supernovae act as sudden, brilliant notes in the cosmic symphony, while clusters of galaxies provide the harmony underneath. Each one contributes a different melody, but together they form a coherent composition, a cosmic score written across space and time. There's something quietly reassuring about how all these methods align. Despite using different instruments, wavelengths, and physical principles, they all tell the same basic story. A universe that began hot and dense, expanded and cooled, grew structure under gravity, and now accelerates under the influence of dark energy. The details continue to sharpen with every new telescope and survey, but the broad picture has remained remarkably robust. In the end, measuring the universe isn't just about numbers, it's about trust. Trust in the methods, trust in the consistency, and trust in the fact that nature's patterns can be understood through patient observation. Every cross-check, every agreement between independent approaches is a quiet affirmation that we really do understand something vast and profound. The next time you hear a cosmologist say the universe is expanding at about 70 kilometers per second per megaparsec, remember that behind that neat little number lies an orchestra of cosmic evidence. Light bent by gravity, galaxies stretched by expansion, supernova dimmed by distance, and ripples frozen in space since the dawn of time. It's an extraordinary achievement, born not of one grand revelation, but of countless small harmonies adding up to a single elegant truth. Science, at its best, is a conversation between what we think we know and what the universe gently corrects. Every time the data disagree, scientists lean in closer, not to argue, but to listen. That's exactly what's happening right now with one of the most famous and most politely debated mysteries in modern cosmology, the Hubble constant tension. The Hubble constant is the number that tells us how fast the universe is expanding today. It connects distance and velocity, describing how galaxies move apart as space stretches. It's not a constant in the eternal sense, just a value measured at this moment in cosmic time, but it's a cornerstone of cosmology, shaping our understanding of the universe's age, size, and future. And here's where the puzzle begins. Depending on how you measure it, you get two different answers. If you use the early universe approach, looking at the cosmic microwave background and interpreting its patterns through the well-tested cosmological model, you get one value, about 67 kilometers per second per megaparsec. That means for every megaparsec of distance, around 3.3 million light-years, a galaxy appears to move away about 67 kilometers per second faster. But when astronomers use the late universe approach, measuring distances to nearby galaxies directly, using supernovae and other distance markers, they find a faster rate, closer to 74 kilometers per second per megaparsec. The gap between those numbers might not sound dramatic, but it's big enough to make cosmologists pause. The two measurements are precise, based on years of careful observation, and the methods are independent. They should agree, and yet they don't. This mismatch is what's now known as the Hubble tension, and it's become one of the most discussed topics in modern astrophysics, not because it's alarming, but because it might be pointing us towards something new. To understand why this matters, it helps to imagine two historians writing a biography of the same person, one studying the early childhood diaries, the other interviewing them as an adult. If both historians are accurate, their timelines should line up perfectly. But if one says the person was born in 1 year and the other insists on another, you know there's a missing page somewhere. The challenge isn't to decide who's wrong, it's to find out what detail everyone overlooked. So where could that missing page be? There are a few main suspects. The first possibility is that one or both sets of measurements still contain small, unrecognized errors. Measuring distances in the universe is notoriously difficult. even with today's sophisticated techniques, each step in the distance ladder, from Cepheid variable stars to supernovae, depends on calibrations that could introduce subtle biases. Likewise, interpreting the cosmic microwave background involves assumptions about the early universe's composition and physics. A small, systematic offset in either method could explain the discrepancy without requiring any exotic new physics. The second possibility is that the models we use to interpret the data might need a gentle tweak. The early universe value of the Hubble constant isn't measured directly. It's inferred from the shape and temperature of the cosmic microwave background through our standard cosmological model, known as lambda CDM. That model assumes dark energy behaves in a particular way, that neutrinos have very small masses, and that no unexpected ingredients lurk in the cosmic mix. If any of those assumptions turn out to be even slightly off, the inferred expansion rate could shift. Perhaps the dark energy isn't perfectly constant, or perhaps there were subtle interactions between radiation and dark matter in the early universe. These ideas are speculative, but they show how open-ended the investigation remains. And then, of course, there's the third possibility, the most exciting, if also the most cautious. Maybe something truly new is going on. The Hubble tension might be a sign that our understanding of cosmic expansion is incomplete. Some theorists propose that dark energy's properties changed over time, becoming more influential earlier than we thought. Others suggest an extra component in the early universe, sometimes called early dark energy, that briefly altered the expansion rate before fading away. There are even ideas involving new types of particles, or changes in how gravity behaves over cosmic distances. These models don't replace the existing framework. They add gentle layers to it, explaining why the numbers diverge without throwing out everything that already works so well. The truth is, this kind of puzzle is exactly how science advances. The Hubble tension isn't a crisis, it's an opportunity. It reminds scientists that the universe is under no obligation to fit neatly into our current theories. When measurements don't agree, it's not a sign of failure but of progress. It means the instruments are good enough, there's data rich enough, and the questions sharp enough to reveal the edges of what we understand. The mood among cosmologists is, appropriately, one of curiosity rather than alarm. Some compare the current situation to standing at the edge of a map that's already remarkably accurate but not quite complete. You can see the coastline, but the finer details inland remain hazy. The task isn't to redraw the entire map, it's to sharpen the contours. Every new telescope and survey adds a little more clarity. Upcoming missions promise to help. The James Webb Space Telescope is already refining distance measurements by observing Cepheid variables and supernovae in unprecedented detail. Meanwhile, large-scale surveys like the Vera Rubin Observatory and the Euclid mission will measure cosmic expansion in entirely new ways, through gravitational lensing and the clustering of galaxies. These next-generation observations might resolve the tension or deepen it. Either outcome would be valuable. Even if the disagreement persists, it's important to keep perspective. Cosmology has an extraordinary track record of self-correction. Over the past century, our picture of the universe has expanded from a static, starry sky to a dynamic cosmos filled with dark matter, dark energy, and light from the beginning of time. Each apparent contradiction along the way, each wrinkle in the data, has led to a deeper, more accurate understanding. The Hubble tension may one day join that list, another clue that guided us toward new physics or refined models. It's also worth remembering that this debate happens in a spirit of cooperation, not conflict. Teams using different methods share data, compare calibrations and check assumptions. Conferences devoted entirely to the Hubble constant often end not with arguments, but with laughter at the irony of trying to measure something so fundamental and finding the universe playfully keeping it secret. The process is patient, meticulous, and humble. Science at its most human. In the end, what makes this story so beautiful is its balance of precision and mystery. We can measure the age of the universe to within 1%, yet there's still room for wonder. The disagreement between 67 and 74 kilometers per second per megaparsec doesn't shake the foundation of cosmology. It adds texture to it. A reminder that even in a field defined by grand scales and enormous numbers, the smallest differences can whisper the loudest truths. The next time you read about the Hubble tension, don't picture scientists in despair. Picture them smiling, poring over graphs and spectra, aware that they're glimpsing the edge of the known. The universe has thrown them a gentle riddle, and they're doing what scientists have always done, listening carefully, adjusting the instruments, and enjoying the thrill of not yet knowing the answer. Every grand idea invites company. The Big Bang model, elegant though it is, has never stood completely alone. From the moment it was proposed, scientists and philosophers alike have wondered, did the universe really begin from a single fiery moment? Could it have always existed, changing form but never truly starting or ending? The history of cosmology is full of imaginative alternatives, some long set aside, others still being refined, and together they reveal one of science's best qualities, its willingness to listen to competing stories until the data choose a winner. In the mid-20th century, not everyone was comfortable with the idea of a universe that had a beginning. The notion that time itself might have a starting point felt, to some, more theological than scientific. In 1948, 3 British physicists, Fred Hoyle, Hermann Bondi and Thomas Gold, proposed a different vision, the steady-state theory. In their model, the universe expands, yes, but its overall appearance never changes. As galaxies move apart, new matter continually forms to fill the gaps, keeping the density constant. The cosmos, in this view, had no beginning and no end. It was eternal and self-sustaining. The steady-state model was elegant in its simplicity and philosophically appealing. It eliminated the awkward question of what came before, replacing it with infinite continuity. For a time, it competed seriously with the Big Bang idea. Both models predicted an expanding universe, but only one could explain the specific details emerging from observation. The balance tipped dramatically in 1965 when Arno Penzias and Robert Wilson discovered the cosmic microwave background, the faint afterglow of a hot, dense, early universe. The steady-state theory couldn't account for such radiation, while the Big Bang predicted it almost perfectly. It was one of those moments when nature gently but firmly closed one chapter and opened another. Hoyle, Bondi and Gold had imagined an eternal universe, but the evidence pointed to a cosmos with a fiery beginning and a long, evolving history. Still, the desire for a universe without edges or singularities, the infinite something rather than the unsettling nothing before, never quite went away. Over the decades, new models have emerged, each trying to smooth the rougher parts of the Big Bang story. One of the most intriguing families of ideas involves cyclic or bouncing universes, where expansion and contraction happen in endless succession. Instead of beginning with a singular explosion, the cosmos might have collapsed from a previous state, bounced at its densest moment, and then expanded again. In some versions, this process repeats forever. Bang, expand, cool, contract, bounce, an eternal heartbeat of creation and renewal. The appeal of these models is easy to see. They neatly sidestep the question of before the Big Bang by suggesting there was a before, just of a different kind. They also offer ways to explain certain puzzles, like why the universe is so uniform, without invoking a brief period of inflation. The ekpyrotic model, for instance, proposes that our Big Bang was triggered when 2 higher-dimensional brains, vast sheets of space in a larger dimensional universe, collided. It's a beautiful concept, blending cosmology with the speculative mathematics of string theory. However, these ideas, as elegant as they are, face their own challenges. The universe leaves fingerprints on everything it does, and those fingerprints have to match what we observe. The cosmic microwave background, for example, provides a detailed record of the conditions in the early universe. Inflation, the rapid expansion model within the standard Big Bang framework, explains those patterns extremely well. Any alternative has to do at least as good a job, and so far no cyclic or bouncing model has matched inflation's success across the full range of observations. Some versions predict features in the CMB that we don't see, while others struggle to produce the right amount of structure in galaxies and clusters. That doesn't mean these ideas are wrong, just unproven. The difference between disfavored and dismissed in science is enormous. When cosmologists talk about alternatives, they usually do so with a sense of humility. The universe has surprised us before, and it may again. Many once discarded ideas have returned in new guises after better data or deeper understanding. Even inflation itself began as a speculative fix to a few early puzzles before becoming a cornerstone of modern cosmology. If future observations uncover signatures that don't fit the standard model, subtle patterns in the polarization of the CMB, or evidence of a previous cycle written into gravitational waves, these more exotic possibilities could take center stage again. Another modern contender explores whether the universe might not have started with a true singularity at all. Quantum cosmology, still in its infancy, seeks to describe the birth of the universe using the rules of quantum mechanics. In some approaches, the Big Bang isn't a sharp beginning but a transition, a shift from a prior quantum state of space-time itself. In these scenarios, before doesn't mean time stretching backward. It means a realm where time, space, and matter as we know them simply didn't exist yet. What replaced them is still up for debate. Perhaps a quantum foam of possibilities, or a timeless wave function describing all potential universes at once. These models remind us that our picture of the cosmos is always evolving. The Big Bang remains the most successful framework because it explains so much so well. The cosmic microwave background, the abundance of light elements, the expansion of space, and the large-scale structure of galaxies. Yet even within this framework, we know it's not the full story. It doesn't describe what caused the bang, or what the universe was like in the first fraction of a second when gravity and quantum mechanics collided in mystery. In that sense, the alternatives aren't rebellions against the Big Bang. They're extensions, attempts to reach further back into the unknown. Every competing model teaches us something. The steady-state idea sharpened the Big Bang's predictions and inspired deeper searches for evidence. The cyclic and bouncing models push physicists to consider what might happen if time itself loops. Quantum cosmology forces us to confront the boundaries of our equations. None of these paths are wasted effort. Science is not about picking one answer and declaring victory. It's about keeping multiple possibilities alive until nature narrows them down. There's a quiet grace in this process. Scientists know that every theory is provisional, no matter how elegant. The universe doesn't owe us simplicity, it owes us honesty. As new telescopes probe deeper into space and earlier into time, we'll keep refining our models, testing them and adjusting when necessary. Perhaps we'll find traces of a prior universe hidden in the cosmic background. Perhaps we'll confirm that the Big Bang, with its inflationary flourish, really is the simplest and most accurate description. Either way, the data will decide. It's worth remembering that disagreement in cosmology isn't a sign of confusion, it's a sign of vitality. Competing models keep the field alive and flexible. They give young researchers questions to chase and old ideas to challenge. The steady-state model may have faded into history, but its spirit of curiosity lives on in every new attempt to stretch our understanding further. And if one day we discover that the universe didn't begin but transformed, that time has no ultimate starting point, then the story will be richer, not poorer. Science thrives on revision, on being proven wrong in the best possible way. Whatever the final model turns out to be, it will rest not on belief or persuasion, but on the patient accumulation of evidence. For now, we can admire the Big Bang for what it is, a model that has stood firm through decades of scrutiny, while still leaving space for wonder. The cosmos continues to whisper new possibilities, and scientists continue to listen. Whether the universe began with a bang, a bounce, or an eternal rhythm of renewal, the journey toward understanding it is the most human story of all, a story written in data, humility, and the quiet joy of asking again and again, what if? The question comes as naturally as breathing. What came before the Big Bang? It's almost impossible not to ask. Every story we know has a beginning, so it feels intuitive that the universe must too. Something must have caused it, right? Some spark, some before that gave rise to the first moment of time. But here's where language and intuition begin to falter. The closer we try to peer toward that before, the more physics gently suggests that the question itself might be misplaced. According to general relativity, time and space are not separate ingredients floating in an empty background. They are part of the same fabric, woven together by energy and matter. The equations that describe the universe tell us that space can stretch, bend, and twist, and time stretches and bends along with it. So when we talk about the Big Bang, we're not describing an explosion in space. We're describing an expansion of space and time themselves. The Big Bang isn't just where the universe started, it's where the concepts of where and when start to make sense at all. That's what makes before the Big Bang such a tricky idea. If time itself began with the Big Bang, then asking what came before is like asking what's north of the North Pole. You can walk in any direction and find south, but there is no direction called north beyond that point. It's simply where the map stops being meaningful. The same may be true of time. The Big Bang is not an event in time, it's the boundary of time as we know it. Of course, that doesn't mean curiosity stops there. Scientists, being human, can't resist peeking past the edge of the map. The equations of general relativity work beautifully almost everywhere, but as you approach the Big Bang, when densities and temperatures become extreme, they begin to break down. They predict a singularity, a point of infinite density where the mathematics collapse into nonsense. Infinity in physics is usually a signpost that says you need a new theory, and that's where quantum mechanics enters the picture. We know that, at very small scales, the rules of quantum physics govern everything. Particles blur, probabilities replace certainties, and fields fluctuate with restless energy. But gravity, the curvature of space-time, has never been successfully described in quantum terms. We have separate equations for the very large, Einstein's general relativity, and the very small, quantum mechanics, and both are spectacularly successful in their own domains. Yet at the beginning of the universe, where the small and the large collide, neither theory can stand alone. What's needed is a theory of quantum gravity, a framework that unites the two and describes the earliest moments without falling apart, so far that grand unification remains out of reach. There are contenders, string theory, loop quantum gravity, and others, but no final answer. Each suggests that the Big Bang singularity might not be a singularity at all. In some versions, the universe bounces from a prior state, avoiding infinities. In others, space-time becomes fuzzy, and the question of before dissolves into quantum uncertainty. The frontier is open, but the signposts are faint. Still, This uncertainty is not a failure, it's an honest frontier. Science has always advanced by reaching the limits of what current theories can describe. Just as Newton's laws gave way to Einstein's relativity when speeds approached that of light, our current models will eventually be refined by a deeper understanding that merges the classical and quantum worlds. For now, we can see the edge clearly, we just can't yet see past it. Interestingly, even without a complete theory, physics offers a few glimpses of what that edge might look like. Some cosmologists suspect that before what we call the Big Bang, there may have been a prior universe contracting inward, a big bounce. Others propose that our universe could have budded off from a larger multiverse, like a bubble forming in a cosmic foam. In these ideas, the Big Bang wasn't the beginning of everything, but rather a transition within something larger. It's a bold notion, but so far it remains speculative. The data we have, cosmic microwave background maps, galaxy surveys, particle physics experiments, all trace back confidently to a few fractions of a second after the Big Bang. Beyond that, the trail fades into mathematical mist. Even the word origin becomes slippery at this point. We tend to imagine time as a line, past stretching behind, future extending ahead. But near the beginning, that line may fold or blur. Time might not be fundamental at all. It could be an emergent property of deeper physics, something that arises only when the universe becomes large and cool enough for clocks, causes, and effects to make sense. In that case, asking what came before time might be like asking what came before temperature in a world that hasn't yet invented heat. And yet, there's something quietly beautiful about that limit. It's humbling to think there are places where even our best theories must stop and admit uncertainty. The horizon of understanding doesn't shrink when we meet its edge. It expands, inviting new questions. The mystery of before may never be fully answered, and perhaps that's part of the magic. Philosophers have long noticed that the question of beginnings blends naturally into questions of meaning. If time began with the Big Bang, then the universe may be self-contained. No external trigger, no outside cause, just a self-sufficient unfolding of physical law. That can feel either liberating or unsettling, depending on your temperament. But science, careful and modest, doesn't try to settle philosophical moods. It simply traces what can be measured and acknowledges what cannot. Whether you interpret the boundary as a miracle, a fluctuation, or a feature of reality's deeper geometry, the shared truth is that everything we know flows from it. Even the concept of nothing becomes slippery here. We tend to picture nothingness as empty space, but space itself is something. True nothingness, without dimensions, time, or potential, may not even be possible. Some theories suggest that the universe could have arisen from a quantum fluctuation within a larger timeless field, a spontaneous event with no cause in the classical sense. In that view, nothing may be more like a fertile stillness, a state where existence and non-existence mingle as possibilities waiting for realization. It's less a void than a canvas, one that naturally gives rise to patterns. There's a certain comfort in that idea too. The universe doesn't necessarily need a spark or a hand to set it going. Its laws may carry within them the capacity to generate themselves. That's not to say the mystery disappears, only that the mystery changes shape. Instead of asking, what made the universe? We ask, why do the laws exist at all? And that's a question that might live forever on the border between science and philosophy, between calculation and contemplation. When you trace the cosmic story back to its first instant, you eventually reach a place where mathematics blurs into wonder. Beyond that point, questions may still exist, but their answers might not live in numbers. And that's okay. Some mysteries are meant to stay open, to remind us that curiosity itself is one of the universe's most astonishing products. So what came before the Big Bang? Maybe nothing. Maybe everything. Maybe something so different that before doesn't apply at all. Whatever the truth, it's hidden just beyond the horizon of our equations, waiting patiently for future explorers. For now, we can rest in the knowledge that the universe has revealed much and kept just enough secret to keep us dreaming. The story of time's beginning ends, fittingly, with a pause, a quiet acknowledgement that our understanding, though vast, is still young. Somewhere beyond that first moment lies a truth we can almost feel, but not yet describe, and that is the kind of mystery worth keeping, gentle, humbling, and perfectly suited for drifting to sleep under the same ancient stars that once emerged from the universe's very first dawn. Tonight's journey has been a quiet retelling of the universe's loudest story, not with explosions or special effects, but with patient, careful measurements, redshifts gathered like seashells, faint ripples mapped in ancient light, and the fragile chemistry of the first minutes read from atoms older than any star. Piece by piece, the cosmos allowed us to listen back through time until the noise of everyday life faded and the earliest notes of creation could be heard again. 3 simple pillars held up this tale. First, expansion. Galaxies receding in proportion to their distance, their light stretched until even its colour whispers that space itself is growing. That steady pattern, traced across billions of light years, is the universe's most unassuming confession. It is not what it once was. Second, the oldest light, the cosmic microwave background, still drifts through every room you've ever slept in, a cooled echo of the moment the fog cleared and photons could finally roam free. Its tiny temperature ripples, only millionths of a degree, carry the blueprint of all future structures. Third, the first chemistry, a universe hot enough, briefly enough, to cook a quarter share of helium and a trace of deuterium and lithium, then cool so swiftly that the recipe froze in place. When we test those abundances in pristine gas and ancient stars, they match the predictions like notes aligning on a staff. Taken together, these clues let today's sky confirm yesterday's fire. The galaxies drift, the baby picture painted in microwaves, and the light elements left from the universe's first workshop are independent stories that rhyme. Each was discovered by different instruments, argued over by different teams, and yet when their numbers are laid side by side, they point to the same dawn. The Big Bang is not just a headline, it is a careful chorus, measured softly, again and again. And still, some edges of the map remain invitingly blank. The exact rate of expansion today hums 2 slightly different tunes. Dark matter shapes what we see, but will not show its face. Dark energy leans into the future with a pressure we do not yet understand. Even the question of before lingers like a star beyond the horizon. Felt, perhaps, but not quite seen. These are not failures, they are open doors. In science, the unknown is not a void, but a room with the lights turned low, waiting for our eyes to adjust. So let the instruments rest for now. Imagine the first light, once blinding, now stretched thin by time into a gentle microwave glow, washing silently over the walls. It threads through the spaces between breaths, slips across the window pane, and settles like dusk upon everything you know. All of history is in it. The first ripples, the first atoms, the first sparks that would one day become suns and seas and the soft ticking of a bedroom clock. If you close your eyes, you might even hear it, not as sound, but as a feeling that the world is larger, older, and kinder than it seems at noon. A story begun in heat and haste has become a lullaby of numbers, steady and sure, carrying you towards sleep. In the hush between moments, the universe remembers how it began.